Okay, it is 9 a.m. sharp. So without further ado, let's get started. So my name is Wei Ming, and welcome everyone to the final day of the conference. This morning we'll have, in the morning we'll have 5 talks. Each talk will be 30 minutes, hopefully 20 minutes presentation plus 10 minutes of questions. Presenters, I leave it to your control how much time you want to leave for questions. I would give you a heads up when you at 25 minutes. I will have to interrupt you when the 30 minutes is up. So please be aware of time. First up, we have Luis Lopez from National Snow and Ice Data Center. His presentation title is Earthaccess, a Python library for easy access to NASA cloud data. So welcome, Luis, take it away.
All right, can you hear me all right?
Yes.
Perfect. Yeah, my name is Luis Lopez, and I'm a software engineer at NSIDC, which is in Boulder, although I'm working remote since the pandemic. NSIDC, it's a research institution that it's part of 12 distributed archive data centers that NASA has, NASA Earth Science, for storing data that it's collected, and I'll explain in the next slide. But most of you probably are familiar with NSIDC, and if not, it's right there in Boulder. It's associated with CIRES and the University of Colorado and NASA and NOAA. This collaboration started over a year ago with OpenEscapes, which is one of the initiatives that NASA it's supporting to migrate scientifics or science in the cloud. And I've been working for NSIDC for like over 9 years now. And I'm really glad to talk about this topic because I believe that it's really important. So here's kind of the overview, right? Most of you are aware of cloud computing, and like a lot of research institutions are moving their data to the cloud if they don't have it there already. And it's not as simple as it seems, as you probably also are aware of. NASA started moving all their scientific data to the cloud, and it's projected to be totally migrated in less than 5 years, and it's going to be petabytes of remote sensing data mainly. And this is awesome because, as I said, up until recently, or even now, if you're a researcher and want to get some data from different satellites, and you basically have to go to different data centers, distributed archive centers from NASA, and download probably the same data from the same satellite, but it's fragmented among different data centers. So you probably have to go to NSIDC, and then you go to Oak Ridge National Laboratory to get probably something similar, and it's kind of like an issue. So that's basically why we started this. NASA started this initiative of like supporting scientists migrate their workflows to the cloud because it's sometimes complicated. So I really like this tweet from somebody that works at NASA. And probably you're familiar with the pain of getting data, not just, and this is not a NASA problem. You can see this in every major research institution, that getting to the data is not as simple as it should be. Sometimes that, produces frustrations in the users, like, okay, so just get me the data. And you have these convoluted ways of getting to the data. And this is important because we want to have open science, and one of the foundations of open science is to have data accessibility, or what is now called fair data, right? Which is findable, accessible, and reproducible, and all that stuff. That's, I think, the foundation for, like, if you're going to publish a paper, I really would like to have the data to reproduce the same results. So you have the data, you have the code, and then you can get to the same thing. And that is the way to go. This year has been called the Year of Open Science by NASA. And there are a lot of initiatives right now trying to make this a reality. But we're going to get there. So one of the issues that this Python package tries to address is that if you're new to this world, you have to get up to speed with a lot of different acronyms, a lot of different systems, different APIs. So it's not as simple as, okay, so I'm gonna go to this data center, I'm gonna click or use like a download utility. It should be that simple, in my opinion, but sometimes, systems grow too complex for their own good. And now if you're, as I said, a newcomer to the world of getting data, you have to first say, well, I'm interested in this data set. Do I care if I need the data gridded or a higher level processing? Do I care if there is a threads or open that server serving that data? And if not, how can I get to the files or granules? And once that you get to the granules, then you have to be familiar with the data logins that NASA uses for access, for granting access. And now, on top of that, with this migration to the cloud, some scientists will have to be aware of like, oh, this is in a S3 bucket and it's a cloud storage, and it's not the same thing as a simple. It basically is the same, but it's not the same. And so for a software engineer, that is not a trouble. Like, well, it is, but you can cope with those technicalities. But if you're not a research or a software engineer, it can get complicated. And in OpenScapes, we notice that when we have our cohorts of scientists trying to replicate a paper or accessing the data, sometimes you spend a day just setting up the environment and explaining, oh, by the way, you have to log in using these credentials and these other credentials, and it gets gloomy. And here comes the cloud. So this is a fantastic slide by Patrick Quinn, one of the software engineers or architects at NASA, as this. And they were tasked about with the task of finding out why in the cloud things, when NASA just released we have data in S3 buckets, and a lot of complaints came because it's not as simple as just getting the data because of these different reasons. Like if you find that a particular data set, it's available in the cloud, you have this S3 URL that indicates that you have access to that file. So you want to retrieve the file and say that you're working in an EC2 instance in a virtual machine in Amazon. First thing is, oh, I'm getting an error. Why? Oh, because it's only served if you're in the US West 2 region. So that's one of the Amazon regions. Then, okay, let's get an account. Let's get a compute instance in EC2 in the right region. Okay, can I get the data? Oh, you cannot, because the different DACs have different endpoints, and it's kind of like, oh, so this data is from PODAC, or it's from NSIDC, or it's from a different data center. So they are and this has its explanation. So it's not just like, oh, they occur to do this way, but then you learn like, okay, so this data has this endpoint, this other data, I have to get the credentials. And by the time the user actually gets to the data, I mean, like, I understand the frustration totally. And in here it says 1 hour later, but a coworker said like, oh, that's optimistic. And at the end, you have to translate all of these complications into your workflow, which means like a lot of boilerplate will be, if you see the notebooks that use NASA or data, like you have 2 pages of just dealing with getting the data, like finding the data, getting the links, configuring the credentials, and finally getting to the data. But then you see the notebook and it's doing a lot of stuff that is not related to the actual science in hand. So because of all of these problems, and in the context of this collaboration with OpenScapes, we started to say, well, we need to have a library that abstracts all these, hurdles that the scientists don't need to know about, like, oh, I need to do an HTTP query to CMR. What is CMR? And all of that stuff you normally want, like, I know the data set, DOI, or I know the short name for the data. So just based on that, you should be able to get the data in a programmatic, easy manner. So this is what Earthaccess is about. It's a very young project. It started just a year and a half ago, basically, in a hackathon, actually. So it's a Python library. The reason why it's a Python library is because a lot of the libraries that are used in the geosciences come from the Python world, and specifically from the Pangeo stack. If you're familiar with Pangeo, it's an amazing project that tries to like consolidate community around some particular libraries in Python, like X-Ray, Dask, and the aim is to make the same cloud computing easily and accessible. So if you haven't heard about Pangeo, I highly recommend that you check that out. So that's the reason why we started this, because we were having to deal with all these problems, and we were like, no, this shouldn't be this way. We created the Python library, and you can see here that it's very simple. Before, you had to do all this kind of, boilerplating, saying I'm getting data from this DAC or particular, or I'm in the cloud or I'm not in the cloud. And now it's just like you logging. This is the netRC file. You can have also an access token, which is the way of the authentication will work in the near future. You won't even need to have your own credentials. It's just an access token like any other API. You search for the data. The data comes in, or the results are metadata from this search interface API that NASA has. And then you can basically do two operations. You can download the results, or you can open the results. And if we're talking about higher level products that are gridded, it's amazing to work with X-Ray, because X-Ray understands gridded data, and you can basically only pay for compute because the data is already on S3, so you can stream the data directly into memory. And that can result in like, okay, I have a Dask cluster, I'm going to process all the data. I don't want to deal with the authentication, and you can just open the files and do whatever you want with the computation. And then in the next slide, I'll when to use, right? Because you're probably familiar. Some of these data sets also offer subsetting subsetting services and aggregation services. Earthaccess is not there yet. I hope it will be soon. So if you work at the file level and you don't want like heavy pre-processing of the data, then it's perfect. Because if you're using level 4, where you have a granule represents the whole world, or level 3, and you want to like do a regional study, it's geolocated. X-Ray understands that, and you can like pull the data directly into memory and do your science with 3 lines of code, basically. And the big advantage is that this code will run in your laptop and it will run in the cloud. So you don't have to deal with like, I'm running in AWS, I need S3 credentials, blah, blah, blah. And this is an example that works. This is taken from Jimbo Wang. He's a research scientist at JPL, the PODAC, Physical Oceanography Data Center. And this is reproducing a very famous infographic about sea level rise. What you see in the graph, it's the blue line, it's in situ data from buoys, and the red is satellite data. But with these 3 chunks of code, and I highlighted in red what Earthaccess does, you have data discovery, because the first thing is like, if you don't know, most of the scientists, I think, know what they want and even know the short name for data set that they're looking for. But say that you are interested in just sea surface anomalies or something, right? Keywords, and you can use the DOI if you know it. You get the data set, print the summaries, and search for the granules. And then here you're opening the granules, and Earthaccess is figuring out, oh, I'm running in the cloud, I'm not running in the cloud, and all the credentials and all the authentication behind the scenes. So it just passed to Xarray in the forms of FFmpeg file handlers with the authenticated session. So in this context, it's like if we were opening the files in our local system, although they are in S3. And at the end, you have this amazing infographic with very few cells in a Jupyter notebook. And I think that it's really cool to do that. And in openness case, the ethos for doing this is that we want to make data accessible simpler, because not everybody is a research software engineer. And they don't have to be, in my opinion. Like if you're a journalist and you want to just like verify stuff, like in my opinion, you should be able to like just, run a couple lines of code and get some graphics from the data. And reproducible science with less code, it's more important. It's makes open science more accessible. So you can see that once that you get the data, which it shouldn't be complicated, the complicated part should be in the science, right? Like the data analysis, the transformations and visualizations that have to happen. But we shouldn't complicate the access part. And of course, this is, as I said, a very young project. We're far from done, and this is still a beta. But one of the things that we would like to do is to align the API with Stack, which is a spatial temporal assets catalog spec, which is used by not just NASA, but a lot of institutions to distribute Google Earth Engine and the Microsoft Planetary Computer and other geospatial platforms use that. And make it accessible from the terminal. Right now, it's just a Python library that you can import in your code or in a Jupyter notebook, but it'll be cool to use it from the terminal, so you can like probably use it from a different language. Integrate services like OpenDAP and Harmony. And there are other technicalities like EULAs that some data sets are require the user to say, I accept, the end user license agreement for using the data, especially data that is not from NASA, but it's coming from the European Space Agency, and some restricted data. So those are things that are in the technical side of things that hopefully they will be addressed sooner. In the not technical side of things, I think we need to probably apply for one of those NASA grants to get some money to just keep working on it. It's supported by NSIDC, but it's just partially my time and some other volunteers. And we need a formal review. There is a project called PyOpenSci that does formal reviews for open source projects in Python. It's a fantastic collaboration, I think, that started in Boulder at the Earth lab at CU Boulder. And the most important thing is like we are starting to see people using it and realizing that it actually makes their lives easier. So the most important for me also is get the word out and more people involved in the project. You can install it from pip, you can install it from Conda. It's being used by some people already. We have some collaborators and a lot of people that are not in the contributors per se, but they were critical for the feedback that we got from the scientists when they were doing their science. And that's it. The art was designed by Alison Horst, and she's a fantastic designer in the art world, if you know her. If not, check it out. And that's my contact information. That's my email, and you can find it on GitHub or Twitter with that handle. So that's it. Questions?
Thank you, Luis. We are perfectly on time. We have 10 more minutes for questions. So let me check our in-person audience here. Please come up to the mic.
not a question, but I just want to know if you are migrating to containers-based solutions and providing support for more IO formats, or if you are going towards the GPU as well. So there could be other formats like DALI and all. So are you planning to have those kind of things in your timelines?
Can you repeat the last part? If I'm considering what?
Like, are you going to support, like, I understand you have a file format, like you can read the files and process them pretty well. So do you plan to go towards other formats like HDF5 or maybe some, if you're working on GPUs, maybe you can leverage some Python libraries like DALI and all. So.
Yeah, so Earthaccess is a library that deals with the access in finding the data and accessing the data, but it doesn't understand the format. So basically what it does is to kind of like a driver, if you will. It's a driver for getting the data from NASA cloud, the storage or S3, the S3 buckets, or the data centers, and whatever library you're using. So if it's agnostic from the format. If the data is stored in HDF5, it will just know how to access the HDF5. If the data is stored in SAR, which are a few, it's starting to grow the use of cloud optimized format. So it will just open like a file handler, and it will handle that to whatever library you're using. And for the library, it will be like if the data was in your local disk, although it's in S3. But it doesn't prevent you from opening any kind of format. And the library that you're using could be loading that data into that GPU. So for sure, yeah.
Right now, it's all CPU based.
Yeah, for the most part, what you're looking at here, it's the Pangeo stack works in the CPU, not in the GPU. There are some libraries like Polars, there Rust, that you have options to load the data into GPU and accelerate it. Or there are other like Tai Chi, that it's a language set of Python that it's optimized for running in the GPU. But that depends on the library that you're using for manipulating the data. So it's independent of this library. This library is just for accessing the data. So your library can access data without having to worry about the login and where the data is and that kind of stuff. Yeah.
You have a container solutions as well?
This one doesn't necessarily need a container because it's distributed in a no arch formats, which means that you can run it natively in all of the operating systems. So if you run the pip install or the conda install, it should work in OS X, Windows, or Linux. You can probably create a Docker out of this, but it'll be just another layer that is not necessary for the library.
The last question is, do you have a access limit on the number of logins at a time?
No, there is no limit with NASA. Right now, some data centers limit the number of concurrent connections, which is kind of like, to prevent like denial of service attacks. Like if you want to hit NSIDC and request 100 different times with the same IP, you might get like, throttle. But it's not like it's preventing you from getting gigabytes of data. And that it's free. All of this data is free, and NASA has committed to provide the data for free. So there is no charge. Even if the data is in AWS, you should access it from whenever without charge for the scientists, of course.
Thank you, Luis. Let's continue with our in-person questions. Go ahead.
So this looks like a really great toolkit to kind of ease the use of the S3 buckets in the cloud. And I'm wondering, what does it look like on the server side, where the server is supposed to somehow serve up the metadata for where these buckets exist and how to authenticate to them? And in particular, if I wanted to, say, publish my own data that's stored in S3 or that's stored in just web accessible URLs, how would I go about doing that?
Yeah, so this library so far it's kind of NASA centric. So it knows how to query the common metadata repository, which is the big API that NASA has for searching for data. But one of the thoughts is to make the library more universal with the stack catalog, right? So if we can make that, you can just point your library to your catalog, and you will be basically searching and accessing from your location instead of the NASA location. So that's one of the thoughts, that we can configure Earthaccess to say, use the NOAA stack catalog or use the Microsoft Planetary Computer. That's not there yet. So right now it's only data from NASA, the official data from the S3 buckets and from the DACs, the data centers.
Thanks. Yeah, it's an interesting design to be able to do that, and maybe there's something that I can look in and take away from that. Reproducing that process. Thanks.
Thank you.
Thank you, Luis.
And if there are questions in the chat, unfortunately, when I have the full screen, I don't see the chat. But
I will be also monitoring the online, actually the Slido page. Actually, I don't see any question from the online audience.
And if you have we need people, we need collaborations, you can open an issue on GitHub or just start the repository and say, hey, I would like to, I don't know, find this data set. How would be the Earthaccess way of doing it? And one of the cool things is, like, when you know or you're familiar with all these hurdles that I was talking about, and you see the Earthaccess way, it's like, oh yeah, I see why this is getting popular.
I'll actually have a questions from myself. I once developed a Python package for accessing biomass dataset for, and how does it work for, let's say, integrating new dataset and getting pull request into Earthaccess? Do you have a standard workflow?
Yeah, that's basically the same, or not basically. It's similar to the previous question about, like, how if the data that is not within the NASA realm, how can we integrate things that are not, as of now, there is not a way for Earthaccess to know about other data sets, unfortunately. But this new schema called Stack tries to kind of standardize or federate the search for remote sensing information, and it's widely adopted. So if we can manage to introduce that to Earthaccess, it will be just a matter of configuring it to your catalog and say, well, I'm on top of the NASA data, I want to use this catalog, and it will work similar. Now, most of the data doesn't require, NOAA data doesn't require you to have a login, and that's amazing. But NASA has these restrictions, and that's when users, find a wall sometimes, like, I didn't know that I have and it's free, but you have to register and you have to use, like, an LRC file or a token and blah, blah, blah. So it's coming. I think based on today's feedback, I think we should accelerate that part to make it more interoperable with not just NASA data, but other data.
Sounds like an exciting path. Okay, let's give another round of applause to our speaker, Luis Lopez. Thank you.
Sure. Thank you.
Okay, next up, apologies if I tanked the name. Our presenter is Agrim Sachdeva from Indiana University. The title of the presentation is User Profiling for Personalized and Proactive Developer Security Awareness Training, a Dynamic Graph Embedding Approach.
I'm sorry, I'm just going to take a second to share my screen here. And I hope you can hear me as well as see the screen.
Yes, we can both hear you and see you and your slide.
Perfect. Well, thank you so much for this opportunity to present. Today, I'm going to be presenting my work that looks at personalized and proactive developer security awareness trainings, but specifically in the context of open source software. And I am very thankful to my co-authors, Ben Lazarine and Dr. Samtani from Indiana University, Kelley School of Business, as well as Dr. Zhu from the University of Texas at San Antonio. So hopefully in the next 20 minutes, I'm going to be able to cover everything here in terms of introducing what and why the problem is, the reason we're studying it, the research design that we're using, as well as how we are operationalizing it or how different stakeholders can operationalize the IT artifact that we're proposing, and some future directions. And of course, after that, I would be very happy to take any questions and receive feedback. So open source code, the previous presentation was a great example of how it serves as critical infrastructure for and enables a lot of exciting developments for a lot of the global economy and services and technologies such as banking, healthcare. There is an estimated more than $100 billion impact of open source code. And many scientific CIs and their users, they host and share their research code on social coding repositories such as GitHub. And we see that these social coding repositories are especially susceptible due to distributed development or evolving risks. And most of the vulnerabilities that are introduced are caused due to human error. So we see in Figure 1 and Figure 2 that both the time to detect a vulnerability as well as the increasing number of open source components leads to a compounding problem. So one of the most important mitigation strategies that we can use is early detection or shifting left. So if we can predict the introduction of vulnerabilities by users, that would allow for a lot of personalized as well as timely user trainings. So I hope everybody here is familiar with a typical GitHub user and their activity, but if not, we're just going to take a couple of seconds to go over what activities or interactions on GitHub look like. So say, for example, there's users or collaborators that are working on different kinds of repositories. I take the example of 3 open source repositories here that belong to a scientific CI that is funded by NSF. And there can be multiple kinds of interactions. So they could fork a repository, but they could also introduce vulnerabilities such as push with some sort of hard-coded expressions. And similarly, other users would also be interacting with those repositories. Now, the task that we want to take on here is, given all of these interactions, as well as the propagation of information between these users, can we predict if at some point a user will introduce a vulnerability? So with that in mind, the reason that we want to do this is because current security or education, training, and awareness research, it doesn't comment on open source software security awareness trainings or the timing. And we know from previous research that personalization and timing are very important to security awareness outcomes. Otherwise, it can cause training fatigue or information overload. And if we were to use baseline link prediction techniques, that is not going to consider a lot of unique characteristics of open source software, as well as the context that we're studying, such as the severity of the vulnerabilities or different users. Because of how connected they are, they can have different relative influences. So with that in mind, the 2 research questions that we try to answer are, how can we predict the introduction of vulnerabilities by users into repositories while accounting for information propagation between users, and how we can adapt existing dynamic graph link prediction methods to incorporate all the factors that are going to predict our ability to accurately predict, such as rich feature sets and from users, repositories, as well as vulnerabilities, and capture the relative influence of high-risk repositories as well as actors. So we present our overall research design in figure 5 here. The first step is collecting data. So based on the organization, say, for example, Cyber's NCAR, we would collect all the repositories, and we could also collect, say, for example, forks or repositories on GitHub that if we search or are associated with a certain organization. In this research, though, however, we only collected the repositories that were created by that specific organization. The next thing that we do is scan for vulnerabilities using open source vulnerability scanners, and that is based on the language that is used. So one of the languages that we see used mostly was Python. So we used Bandit, and we also used Flaw Finder and GitHub and Trufflehawk to look for different kinds of vulnerabilities, such as hard-coded secrets, passwords, cross-site scripting attacks, insecure functions, and so forth. So once we scan for vulnerabilities and match them to the user based on the level of the commit, we can create an interaction graph. So it lends itself very readily to a user introducing a vulnerability into the repository, user introducing the vulnerability into the repository. So that is what the edges represent. Once we create this interaction graph, we generate the embeddings using the model that we propose. So the dynamic graph representation learning model that we propose has two novelties that we will get into later. And once those embeddings have been generated, we can perform a downstream task, which is link prediction. So in the overall study, we perform different experiments to benchmark it against recurrent neural network-based methods or attention-based methods. We perform ablation analysis. But in the interest of time and so that we can highlight the practical implications, I'm just going to be going into the case study today. So the data collection, as I highlighted, was from Cyber's, where we collected 99 repositories. There were 395 users that had contributed to it, and our scanning revealed 12,680 vulnerabilities. As well as NCAR, we collected 77 repositories spanning 176 contributors, and our scanners returned 3,326 vulnerabilities. So Table 1 summarizes the key vulnerabilities that are returned from the scanners. We create a user repository bipartite graph, and the edge represents the introduction of a vulnerability. And because we're looking at it in a longitudinal fashion that is taking into account the time dimension, each sequential interaction, we normalize it to 0 or 1. So we have time from 0 to time equals 1. And the intuition behind representing it as a graph is that so we can do downstream tasks like link prediction. So if an edge represents a vulnerability, predicting that edge would represent the prediction of the introduction of vulnerabilities. So there are a lot of features that might help us improve the performance of our prediction. So to make sure that we incorporate these features, we think about it in terms of what are some aspects related to the user that could influence the introduction of vulnerabilities. So we think about the experience, the previous activity of the developers, the frequency and severity of vulnerabilities that they have already introduced, And then we operationalize that, and I will summarize that on the next slide. So similarly, the intuition behind including repository-related features is that there are several characteristics of the repository: the language, popularity, number of people that collaborate on it, number of pre-existing vulnerabilities. All of these can change the propensity that vulnerabilities would be propagated from that repository. And finally, there would be interaction-related features such as the severity of the vulnerability that would be introduced. So how we operationalize this is we think about how the data that is available on GitHub, for example, repositories owned, repository starred, cumulative number of comments, the number of public repositories starred by a user, that could capture different aspects of the factors that influence vulnerability introduction, like their activity, the experience. And we use a similar intuition for the nodal features, where we map the data that is available, the metadata that is available about each of the repositories, and think about what that might represent. So say, for example, vulnerabilities are language specific, so which is why we consider the language, and how much activity there is might be measured by the count of open issues and so forth. And finally, with respect to the edge, the nature of the vulnerabilities associated with each commit would definitely change the risk profile of a developer or a user. So essentially what we're doing in table 6 is trying to map all the metadata that we have about repositories using some sort of rationale about how it would impact the risk carried by it onto different parts of our graph. So the user, as well as repository, as well as edge, and assigning these features to them. So with that in mind, we are going to learn the embeddings of the interaction graph that we have created, such that we can perform downstream tasks. So without going into the math, the intuition here is that vulnerabilities have different severity levels. And so whenever vulnerabilities are introduced and the nodal embeddings, which would represent the risk profile of either the developer or the repository, whenever those are updated, that should take into account the severity of the vulnerability. So a low severity vulnerability being introduced would not make a repository incrementally more risky as compared to a high severity vulnerability being introduced. So what we do is introduce a learnable parameter in the discrete unit to account for 3 different types of edges that reflect the severity of the vulnerability. But essentially, all we're trying to do is improve the quality of our nodal embeddings such that prediction can be improved. The other novelty that we introduce is we know that in this network, different users are going to have differential impact based on their relative position or influence or so forth. So if there's multiple people collaborating on a project, there's bound to be some sort of knowledge, information, a code. I look at somebody else's code, I learned something. I talk to a collaborator, I learned something. So there is propagation of information that the propagation unit is capturing. So what we introduce is this term that takes into account how much influence they would have. And we do that using centrality measures. Specifically, we look at, we look at eigenvector centrality because it captures the transitive influence and prestige score with respect to the entire network. And that can more closely represent teams or other kinds of structures that collaborate on projects within an organization. So both of these novelties, again, the idea is just to improve the nodal embeddings such that we can have better prediction. So when we think about the practical implications, we try to present a case study about that takes into account who the research might be significant for. So say, for example, any managed security service provider could include such an offering in the services that they provide, or internal SOCs within firms. So they would conduct internal security awareness trainings based on the predictions that are produced by this model. And we think about how we could operationalize it, which is the steps that we went through. So collecting the repositories, conducting the vulnerability assessments, creating a graph, training the model, generating the risk profiles, and then finally creating user repository pairs for different periods of time. And then so for any repository plus developer plus time period, we would be able to predict whether or not a vulnerability would be introduced. So just to illustrate what that looks like, we run our model for the first 25% of our data set. So we pretend that if we say that if this model had been run at a certain point, say, for example, the first 1/4 of the time period that we have, then what would have happened if we had taken into account the predictions made by the model? So we see that our model is able to successfully predict that a low severity vulnerability was introduced in this specific commit by this specific user. So what we do is we plot the number of low severity vulnerabilities, that were returned by our scanners, so CWEs 119, 120, 362, and 190 by the same user into the Cyber's repositories over time. And what we see is that if we had, at this point of time, provided targeted security trainings, then maybe there is a possibility that the vulnerabilities that were introduced after, the risk that is associated with them could be mitigated. And just to highlight what that risk may be, we illustrate the low severity vulnerabilities that were introduced by that user. So say, for example, buffer overflow, which could be used to execute arbitrary code or lead to crashes, subvert other security services, or improper restriction of operations within the bounds of a memory buffer, where an attacker can redirect a function pointer to their own code, or can also provide attacker access to sensitive information. So in conclusion, we already have an important administrative control to better protect our organizational assets, which is security training. However, current approaches can lead to training fatigue. They're not personalized and therefore not as effective. So with that in mind, we developed and proposed a dynamic graph embedding representation learning method that predicts the introduction of vulnerabilities. We introduce novelties such as different features, making sure that we account for different levels of severity, as well as the relative influence of developers and users. So that can help us make security trainings personalized and proactive. So some directions for future research could include contextualizing the link prediction. So for example, right now we're looking at users and repositories, but it could also be teams and projects or departments and different kinds of technologies that they're working on. So any combination of contributor and the code base that is being contributed to could be used in the graph, and we could obtain kind of important insights from how a certain group of users could introduce vulnerabilities into a certain group of repositories. And The other thing, which may be a stretch, could be incorporating other kinds of data that is available to the firm. There's prior research that looks at social media data to predict, or communication logs to predict the security risk profile that is carried by a developer. So there could also be other features that we could use, maybe characteristics of the developer themselves, how long they have been at the firm, how long they have been working on a specific project, and so on. So just different sources of data that can be used. So with that, that is the end of the presentation. I would appreciate any questions or comments that you might have that would help us improve the applicability of and the practical implications of our work. So thank you.
Thank you, Agrim, for the presentation and for being on time. We have 9 minutes for questions. I'm just checking. I just posted the link to Slido for the online folks. I encourage you to post your questions. Since we don't have any from the online, I'm going to check in person. Please walk up to the mic.
Yeah, thanks. Interesting talk. I guess, as a, end user of the trainings at NCAR, I'm thinking about how customization might look. Like in your eyes, would it be something like there are different modules targeting different vulnerabilities, and there's like a subset of those that gets presented to a particular person? Or could it even, would it even be customized to use that person's GitHub activity as an example in a training?
So with the current artifact that we propose, we're looking at it at the level of the specific. We're trying to use the characteristics of the specific vulnerability to personalize those trainings. But at the end of the day, what we provide is just an artifact, and how that will be operationalized very much depends on the needs of the organization and what they think is important. So for example, if the organization wants to look at how developers should be educated based on either specific technologies or specific groups of vulnerabilities, or specific types of either severity or specific types, like hard coding, secrets that are hard coded. So those operational decisions, I think, can definitely be undertaken by the firm, and our model would allow for that. With that being said, I think an effective operationalization would be if, based on all of this activity and previous vulnerabilities that have been introduced that we see on GitHub, there is some sort of automated system that, say, for example, an email reminder that would remind a developer to go over a certain module that they have already gone over, or is available at a kind of a central resource when the system predicts that vulnerability or kind of vulnerability might be introduced.
Thanks.
Of course.
I actually have a question from myself. So I really appreciate that the comment you made, most vulnerabilities were not introduced by malicious attempt, but by ignorance. I feel like that's describing myself sometimes. So I would like to, so this is fairly new to me, and I definitely learned a lot. Could you talk a little bit more about, the synergies and distinction from what you have presented and the GitHub blame function? And also, I know that whenever you create a pull request, sometimes there is a automatic checker for your code quality. So do you think how these two components play together with the research and kind of work that you're doing?
Absolutely. So if you don't mind, I would like to uh, share a different slide.
Go ahead.
And because that is definitely a question that we have tried to answer. And what we want to do, I hope you can see my screen right now.
Yes.
So there are a lot of current solutions that GitHub provides, and you're absolutely right in that every year they're improving the kinds of solutions. So they're improving vulnerability scanners and static analysis testing and secret detection. So three product areas that they provide are making sure that any dependencies that the supply chain might have are automatically taken care of. So it could be Dependabot provides automated pull requests, and the code that you're writing is secure. So there's a semantic analysis engine, GitHub um, um, uh, bot code QL, and they integrate it into their security services, and also secret scanning, which is turned on by default. So if there's any tokens or private keys that you put in there, GitHub secret scanning is going to tell you that. So some of the shortcomings are all of these identify vulnerabilities after they have been committed to code. So we're trying to make a push from detective controls to more preventative controls. And the second thing is all of these work at the repository levels and don't focus on users or provide feedback. So there is no the human resource, there is no development that is happening. And while these solutions might be able to take care of that, the developer themselves are not um, gaining any um, education in terms of how to mitigate them by preventing their introduction. And often these systems require extensive configuration. So all of these are code first strategies. And what we're advocating for is a more user first strategy where we're saying they could be more effective, where we already know that security training is more effective than embedded tools and interfaces. Prior research tells us that. But we also know that these trainings lose efficacy and they cause training fatigue. And that's why we're trying to, and that's where the motivation for this problem comes from.
I see. Thank you. I actually have a follow-up quick question. So after you generate the graph, I'm curious whether you had any temporal analysis. So I was interested to see whether you find a specific time period, maybe let's say before Christmas, there is the increase of vulnerability introduction. So did you ever have a chance to kind of look at the temporal analysis of your graph?
So while we take a design science first approach in this to create the artifact, I think this study could definitely be further strengthened or made robust by the kind of empirical analysis that you're suggesting. And I will make sure to do that. I think that is very important just kind of look at the overall trends look at the view from 1,000 feet up before we dive deep into it. And that is very useful feedback that I will make sure I take into account. Thank you.
Thank you. Final check for questions. Okay, let's thank our presenter, Agrim, again. Thank you.
Thank you.
And we are going to take a 30 minutes break, and we'll reconvene at 10:30 a.m. Colorado time. Okay, everyone, it is 10:30 sharp, and I hope you had some time to enjoy some refreshment. And welcome back. So the next presenter is Helen Kershaw from NCAR CISO, Computational and Information Systems Lab. And the talk, the title of the talk is Revamping the Build System for Dart, Enabling Disruptive Science Without Disrupting Scientists. And Helen, take it away.
Hi, everyone. Hopefully you can hear me and see my slides. So I'll kick off. I'm Helen. I'm the lead software engineer in the DARES group. I'm going to talk about revamping our build system. So just some terminology before I kick off. DARES is the group of people. So that's the Data Assimilation Research section. That's the team. There might be a couple of us in the room there. The core team is 7 people, 2 software engineers and 5 scientists. We have various postdocs, students and visitors, and a bunch of external collaborators across our NCAR and the world. And Dart is the Data Assimilation Research Testbed. So that's the software we produce. You can check out Dart and all the stuff we do at dart.ucar.edu and see what projects we're involved in. A small intro about myself. This is where I try and justify why it's worth listening to me, or at least give you some topics to break the ice. If you want to chat to me about software, supercomputing, or geophysics. I have a geophysical science degree from the University of Leeds in the UK, mostly solid earth geophysics. My dissertation was on the secular variation of the Earth's magnetic field. And a small fact, the guy who marked my dissertation was John Mound, who was the scientific advisor on the movie The Core. I can't believe The Core only has 5.5 on IMDb. After graduating, I worked for an airborne geophysical survey company. So we flew gravity and magnetic surveys with small aircraft. Cool. So, you know, collecting data, QCing data. So I spent some time in the field in Peru and Greenland. Much like golf spoils a good walk, fieldwork spoils a nice holiday. So I went off to do a PhD. So I went to graduate school in New Zealand. This is where I got into HBC. I worked on breast cancer detection using digital image-based elastotomography. Cancer is very stiff, so you can detect it in surface motion when you pass a wave through it. Helioseismology, but on tissue. That's how I described it in my application. So cool inverse problems, and I got to run on Bluefern, which is the University of Canterbury supercomputer. So the supercomputer is in a building designed so well, the machine kept running during a 7.2 magnitude earthquake. After a brief stint at a finance startup in Boulder, I joined the DARES team for several years. This was back when IMAGE was a thing, the Institute for Mathematics Applied to Geosciences, and I worked on putting one-sided MPI communication into Dart, so we could run with really big models. I left to work at Brown in the Center for Computation and Visualization, and I led a team of research software engineers there. So we contracted ourselves out to work on various computational projects, including physically informed neural networks, fish behavior, krill DNA, as well as more traditional HPC topics like mechanical engineering and Earth system modeling. And I ran office hours for people to come and chat computation, which is one of my favorite things to do. Any topic, any language, any problem, whoever walked through the door. So too big, not fast enough, buggy, we'll have a go at fixing it. Then I came back to DARES, and here I am now, 2.5 years into my second term. So I have three word takeaways that I would like you to get from my talk. Open source software, research software engineering, ensemble data assimilation. Really, I'd like to communicate the joy of open source software, particularly for science. Just like to put it out there for people unaware, research software engineering is a thing. If you're a scientist and you want to become a software engineer, or you're a computer science student who wants to get more involved into science, come and chat to me. We have NCAR visitor programs to pay for people to do code. And also for anyone who's not already a member, do check out the US RSE organization. And ensemble data assimilation is the coolest computational problem you can be working on. Well, I'll try and convince you on that last one. So ensemble data assimilation, what is it? You take a group of model forecasts, so like 50, 80 numerical predictions with slightly different initial conditions. This gives you like a statistical distribution, so your best initial guess, really. You measure things, so your measurements have errors, and you combine that with forecasts to get a better estimate of what's going on. If you can forecast it and you can measure it, you can use Dart. So in addition to weather and climate, we've had people use Dart for things like flu and COVID-19 forecasting. It's Dart. We're an open source code with a large caveat here, large for scientific software, and lively. There's no caveat on lively, community of researchers. We recently had a full day session at the American Meteorological Society annual meeting devoted to Dart, and it's 20 years of data assimilation. So here's the super condensed rundown of what we do. Computationally, ensemble data assimilation is super interesting. We have to go fast, right? So this is Dart being used in a real-time field experiment. Glenn Romain actually worked on this. He's now a UK science advisor. And so what they were doing is they were flying aircraft at severe weather, drop a bunch of sensors, and then forecast where the severe weather is going to go next. So it's critically important, right? Your data assimilation is finished in time for your next flight. We also deal with like quite large, huge amounts of data. Not only high resolution models, we have an upcoming ASD project on high resolution ocean data assimilation. We also have long running data sets. So this example is a climate reanalysis product produced by the team. It's about 20 years worth of data and counting. It's 80 climate models at once. So you can imagine the challenges you have in doing that. Assimilating observations every 6 hours, and it took about 50 million core hours on Cheyenne. So the eagle-eyed amongst you will notice some interesting load balancing challenges with the location of these observations, irregular in space and time. Talk to me if you're interested in these kinds of problems. And for the data analysis and machine learning folks out there, this data set is available from NCAR, both on the RDA and Amazon AWS. So do take a look if you're interested. And then what we do really is science, right? And it's leading edge science for data assimilation. So real world consequences, really. This is WRF Hydro, and they're interested in where flooding is going to occur when there's a hurricane. So the hurricane dumps an enormous amount of rain, 30 inches. There's a hydrogeological model of where the water is going to go, and a network of stream gauges measuring the flow. So the development of how to use data assimilation in that situation, and you want to take into account the physical constraints like upstream influences downstream, not vice versa, where the water can go and how to assimilate, was all worked out within the Dart framework. So I talked to Mohau Grampty about his work with the USGS, if you want more info on this. And Tony B just presented to Congress about the importance of data assimilation, in particular, why the government should reauthorize the Weather Act and the importance of data assimilation to the USA. So it's very cool. You want to combine observations and models. You want to think about predictability. Data assimilation is a big part of NCAR's mission. And a teaser here, ensemble data assimilation lets you assimilate bounded quantities. By bounded quantities, we mean things like rain. So you can't have negative rain. So this is the blue here. This is the new quantile conserving filter. We'll make sure your probability distributions respect the bounds. Or equally, like it can cope with multimodal things and have ensemble members swap between modes. We have code that you can use now with this, and the more varied feedback we can get earlier in the development process, the better. If you want to collaborate on a use case for this, yeah, reach out. All right, enough introduction. Let's motivate this talk. So joy and pain, that's today's theme. The joy of open source software and pain. So the joy of open source is discovering what people do with your code. So we found out from a colleague that The Space Weather Operational Office of Taiwan is using Dart in production. The Italian Center, CMCC, is working on using Dart in production. Has some really interesting workflow and observation management for satellite obs. We've got WRF-Chem, a fork of Dart, and there's a couple of groups out there using various particle filters that they've added to Dart. Note the bottom right picture has nothing to do with the particle filter algorithm. I just couldn't find a Wikimedia picture to show particle filtering. So one takeaway today is if you want your algorithm visible, you should put something on Wikimedia. So it was a joy to go to AMS, right, and see all the various science happening because of Dart. Because as much as we're building software, right, we're building community. And so Dart's been open source since it started 20 years ago. To illustrate this, here's just a little animation. This is all the files added to Dart in 20 years and 20 seconds. You'll see people making the commits, dancing around. You might see your name pop in there. You can see various refactors. You can see Moha arrive and the impact he makes. And then we kind of had an explosion in contributors in the last year. So lots of challenges dealing with that. So what's the downside of this 20 years of open source software? Well, it's 20 years, right? Lots of baggage. There's some smart choices made over 20 years. The talk I really want to give is 10 things I hate about Dart, or why smart decisions, including sometimes my decisions, drive me up the wall. Also, like a lively, large open source community. What's the downside? You got it right. It's large and lively, and it's open source. So users, they're so annoying. Developers are worse. So it's super easy to change software that no one uses, right? But open source projects have a life of their own. You've got like 92-ish forks, plus the various projects that use Dart and don't fork, just take the code. So this gets me to the title of my talk, right? Revamping the build system. Enabling disruptive science without disrupting scientists, right? The goal is science. So here's the motivation. Picture the scene. It's November 2021. I have a student coming for a summer project. Summer projects such as SciParks, which is the summer internship in parallel computing at CISL. At the time, I get to work on something completely fun. With students, you can go for something really big, potentially impactful projects with no real consequence for failure, right? Try something, learn something, that's the goal. Excuse me. And we do get really smart students. For 2022, this is Ed Liu, a PhD student at Drexel. And so, I want Ed to come along and be able to hack at the guts of Dart and quickly test on various models. So what's the problem? The problem is we have this clunky build system. And let me stress, what's not the problem? This is not a complaint about MKMF. So MKMF is a tool we use. It's a NOAA GFDL product, constructs mix files for you from source code, nothing but praise for MKMF. The problem is the way we're using it. So Dart started out running with one model, one toy model, one global model. Now it's 25 plus models, 40 observation types and growing. It's been working 20 years. It's not that big a deal to add a new model in space, but I want to go faster, right? So here's the problem statement I presented to my group. It's more wordy than clunky build system, but that's what I'm communicating. So there's science changes in the pipeline that are essentially disruptive, but they're only disruptive because of our build system. If you want to split modules with the old build system, you'd have to change hundreds of files. I'll show you this on the next few slides. And so the goal is to not do this, right? We want to be able to refactor code without this horrific tax of altering files. We want to iterate quickly while developing. Does this new algorithm work well for Dart MPass on unstructured grids as well as it does for WRF? What if I separate horizontal location from vertical location so we can speed up range searches? What if? That's the spirit of research engineering. So a user builds Dart for the particular model they're working with. So I think you can see quite a few models here from 9 var downwards. Quite a long list. And the problem was you had to have all these files just to build. So every model for every program. So it's just nuts, right? Just added and added and added each time a new model interface was developed. Just a huge part of the repo. So here's the breakdown of files. It was essentially coming out as about 30% of files in the repo were just for building. So if you need to change those when you're developing, like, no one's going to do that. Let's be realistic. And that's not a good situation, right? You don't want your build system constraining or informing your software design choices, right? I'm not going to split a module because I can't be bothered changing a bunch of files. So I rewrote the build system. I started with a small something a student could use for hacking. And the spoiler is you can do this really easily. You can just pull out all those files, no problem. And it's a joy to remove that much code for my own personal gain, but it got me thinking a little bigger. So I played around for a couple of weeks in between watching supercomputing talks. Remember, this is November 21. Personally, I think 2 weeks is a good period of time for making decisions. The goal is to decide whether a project is a go or no go at that particular time, to find the edges of the parameter space, chat to people, see what they think, have them digest it for a while. Here's our trusty Dart developers flowchart. As a scientific software developer, you always have projects at various stages, and it's super important. Are you solving the right problem? Is it the right time to be doing this? And so after about 2 weeks, I was like, yeah, it is. And so I had a bigger aim. I wanted to release this and replace the Dart build system. The first step is to convince people this is a good idea, and be open to finding out it's not a good idea, and not break Dart in the wild. So in terms of convincing people, what you're always fighting against is the old adage, if it's not broke, don't fix it, right? And more realistically, in open source, there's so many things that need fixing or improving that are orders of magnitude beyond the resources we have. Why should we fix this? And this is perfectly reasonable, right? And prioritizing what to work on is incredibly important for any project. So why is this a priority? Well, there are science changes to Dart in the pipeline that are essentially disruptive changes. Great, yes, joy. This is what we live for as software engineers, right? Line up what you want to do with the needs of the community. So my takeaways: pick your moment, line up your ducks, always have an ulterior motive. Ulterior motive is a bit of a joke here. Have plans, right? There are lots of things you can do with any project. And so you need to be ready to align your needs with your collaborators. Here's the proposal I presented to my group. This is what we need the build system to do. Quick build is the name of it, and currently does. We need to build all our programs, right? We need to build any model specific programs for the 25, 30 models we've got. We need to be able to convert CDL to NetCDF. So Dart's used for a big range of things, right? It's used to teach people data assimilation. It's used, people use it on their laptops with toy models. And it's used, all the way up to Cheyenne and everything in between. And it probably needs to be a script. That's what users are used to. They want to change it. And we need to build without MPI. What I'd like to be able to do is refactor, really. I want to be able to move, rearrange, and split without need to change scripts for, 40 models and 25 converters, or vice versa. And I want to be able to test, right? I want to build everything really quickly, or at least in a reasonable time. And I want to be able to switch out the build system. I didn't propose this originally. We're still using MKMF, but we should make it easy if we want to change to an off-the-shelf build system. So no new requirements. That's mostly, I want to get this in, let us do our things and not break people's code. And one build of preprocess, I'll go over this a bit later, and some precedent rules we could take advantage of. So here's the usage from a user perspective. You still build Dart for whatever model you're using, and you have a quick build.sh rather than CSH. So this is the change from a user point of view. Slightly different script. So we had some additional features we can do now. There's a help, prints the usage, clean, single program build without MPI. The single program build in this example creates a makefile for filter, which you can then code make run if even quick build takes too long for you because you're like me. How it works. So all these MKMF program scripts we had essentially all look like this, right? That's just a function someone's written out hundreds of times. And path names are just the result of someone manually listing the files. So we can do that automatically, right? That's a no-brainer. It's crying out for automation, which means fun with functions. So the Dart source code is assembled, collected together for a given location module. So this might be a 3D sphere, an annulus, a 2D, whatever model people are using, and a given model. MPI or no MPI. Then because we have one-sided communication, we have a couple of options for how you set up the window. Probably we can get rid of this with MPI 3. Again, lively active community. Sometimes we get the strangest support requests from people running on systems they can't upgrade. So we're always a little hesitant to push on. Observation converters are almost the same. They tend to have links to external libraries just because they're ingesting all sorts of data, things like prep buffer data. And if you're going to use functions, you have to have rules, right? So we already have rules. Everyone has rules. And you can find the rules, the hidden rules you have. What are your assumptions? That's always a good question to ask. Rules are mostly about naming. Revamping a build system lets you discover a lot of bugs. So this example, both these programs are called the same thing. So with the old system, you just build the first one in the list. So you have to be super strict about naming modules and programs. If you're like me, honestly, I don't really like being told what to do. I like to see the purpose behind a rule and why we're doing this. So unique names for programs, and that's because MKMF can only generate one makefile for one program at once. Location code, which is compile time choice, just has to have unique names so we can switch it out and find it. And then a couple of sort of oddball rules for the developer code and some specific programs. So the rules are for finding the source code, right? That's all they're doing. So you change the rule, change the function to find the code. And then, of course, we have to deal with a bunch of bits and bobs of non-Dart code and stuff that's crept into the repo. So this clunkiness gets pushed into the internals of the build functions to ignore some code. Should we have these files in the repo? In my opinion, no, probably not. But we have to deal with reality and get to where we want to go first. So we end up with these two sets of functions to build Dart programs, one for assimilation for whatever model, and one for observation converters. Philosophically, this seems like a good split. You could see if the code is going to diverge, the observations to deal with millions of satellite obs a day could end up quite different to your supercomputer assimilation code. You could argue for one set of functions is better, but I think the flexibility this split gives us is the sensible choice for now. Quick build is still a script. We use Git to tell us where the root directory is, and we build all the programs we want. Here's WARF. They have a bunch of WARF specific stuff they've written in all sorts of directories. Just grabs them and builds them, in addition to your regular Dart code. So why does this help? Who cares, right? Add the code, compile any model. We're back to what if, right? That's what you want. Faster testing. And practically just fewer files to review, so prone to error. So we have a shorter time to release. Splitting modules as part of refactors and change your mind later, right? That's really nice because people are different. I like thinking about an idea, having a design review. Some people like to start hacking away to explore an idea. Some people just design by typing. What you get sometimes is, oh, here is 10,000 lines of code from a senior scientist. There's already 3 papers published and we need to ship the code ASAP. Okie dokie. people are different, and our job is to get good ideas into production code. The build functions are all called by quick build, so it lets you change them once for quick build. So new arguments, we want to switch out the build system. We want to use Rust for preprocess or something. To sidestep a bit here and cover preprocess, which is a Dart program. So Dart has a design decision that separates observations from what you're measuring, which is the physical quantity, and the forecast model. So it allows you to mix and match between these, and preprocess is the tool that makes this happen. So it actually writes your code for you. So it's going to instance observation-specific code at compile time. This got moved outside of the work directory, which is what you're building, Dart, because why not? It's not model or convert dependent. And it allows you to take advantage of MKMF's precedence rule. And it's been really good for reducing redundancy. So we have Anderson, who's a student working with us on interfacing CI testing on Cheyenne with GitHub. Pull requests are super nice. We want to build and test as fast as possible. The things I'm worried about, Bash, obviously. Other people's code, I'm always worried about it. Are people doing things we don't expect? Developers versus users. We'd like to turn users into developers. Is it limiting us? So we have to change the functions if we move files. And we're overcompiling. So we're building a little bit more code than we need to. Does this annoy me? Yes. Am I going to fix it? No, not right now. So what has this revamp enabled? We've had a high school student implement this as part of his baccalaureate. So it's much easier to just automate adding a new model interface. So the takeaway here is anyone can make an impact. Please reach out if there's something you want to work on. What's nice is that we're kind of nudging people to add documentation by creating this stub. Do people do it? No, but we can try. Benjamin's documentation is here. So feel free to check it out at docs.dart.ucar.edu. And science-wise, it's allowed us to push forwards with a quantile methods release at AMS back in January. So this is not my work, right? This is Jeff Anderson, who's an AMS fellow. And we have CI scientists working with this code. Super cool. So back to motivation. Why you do something? What is the goal? With open source software, I'm often working with collaborators, right? So this means other people's labor and all the politics that goes along with that. Various incentives from the funding agencies, research goals, personal motivations. People's time has value, and we want people to be spending that time on, the most interesting and impactful thing they could be working on. And my ulterior motive is I'd like them to be working on Dart. So, and Ed, remember Ed? This all started with Ed. He ended up working on reducing memory in super high res ocean models with Cast. So that's the end. Here are the takeaways. Don't write your own build system. I hope no one does that. That's not what this talk is about. Or do it if you want, as your life. Always have an ulterior motive, always have a plan. If you want to change something, measure it. Also connected to this, if you measure it, it will become a metric. So be careful what you measure. If someone's trying to push a metric on you and you want to change things, ask them what their assumptions are. And always ask, is that a big number? The joy of open source, hopefully I've sold you on that. And work on a good team if you can, that lets you try stuff. So join us. Super cool what we do. Like I said, there's visitors programs, internships. I'd really like to get into Google Summer of Code if anyone's interested in that. But yeah, and a plug for my Better Scientific Software project. I have a fellowship to create an online code review tutorial, so please contact me about that too. That's my email, hkershaw, and Dart will get the whole Dart team. So thanks. I think I'm just in time. So I guess any questions?
Thank you, Helen. I think we can have time for quick questions. Let me check the online portal. in-person audience. Okay, and Helen has her, excuse me, sorry. Helen has her contact on the screen, so I encourage you to reach out to her and talk more about data assimilation. Okay, so let's move on. Our next talk is from Brian Vanderwende, also from CISO, NCAR CISO, and the title of the talk is Building a Better HPC User Environment.
Thing here. Sorry if my voice ends up a little funky. I decided to inhale my coffee instead of drink it 10 minutes ago. So, oops. Yeah, so the title of my talk is Building a Better HPC User Environment. And to be clear, it sounds a little more grandiose than I intended, but it's really just talking about evolving our NCAR HPC user environment from what we have on Cheyenne, our current system, to what we'll have on Derecho, our incoming system. So, let's see. There we go. Okay, so yeah, we're in 2023 and we're finally nearing the threshold to transition to using Derecho here at NCAR, which we're excited about. Here's just a little sort of timeline. Let's see, yeah, that shows up okay. So, we had Yellowstone when I first started at NCAR in 2015. So I got to support that system for a couple of years. We've had Cheyenne since 2017, and it's still up and running. It's still producing good science. We have a analysis system as well called Casper that sort of sits alongside, and that's going to keep humming along with some updates and augmentations as we move forward. But this year we're really in the midst of deploying Derecho, and we've been playing on a test system called Gust for a little while, with a kind of a cheeky name there. So a little bit about Derecho for anybody who's not familiar. It's a 19.87 petaflop system, HPE Cray EX. Sounds like there's a few other of those floating around in the audience here. 3.5 times the compute of Cheyenne, so that'll be a nice bump for us. 80% of that compute is provided by CPUs. Still pretty CPU heavy workflow here at NCAR. Those will be AMD Milans. And then 20% is NVIDIA A100 GPUs. And then finally we have 60 petabytes, so quite a bit of Lustre storage on that system as well. So it's a bit about the hardware. How I've been involved is really in the application / user readiness / software deployment side. So I've been heading up our applications team, as we've called it. And our mission on that team is basically to ensure a smooth user experience and ease the transition from Cheyenne, especially considering the fact that this is going to be the first system where we have a significant amount of GPUs. So that's both exciting and made us a little nervous just in terms of having people be ready to use those. The team, it's comprised of different members and perspectives across our Computational Information Systems Lab, CISL, here at NCAR. So we have some folks who are like me, who are kind of, on the support side, and then we have some folks who are more on the development side. And that's been a nice co-design collaboration. What we're doing is we're putting significant focus on new workflows, but we still want to maintain hopefully a high level support for traditional use cases. And I guess, these are all sort of becoming traditional, but when I made this slide, it seemed a little more novel. So, thinking about like modern technologies, you've got like machine learning libraries, trying to burst out to the cloud from the system, using containers. People have already gotten really excited and really embraced Jupyter Hub at NCAR, so we want to keep that going well. But then again, having that traditional environment as well. And I'm going to, I guess, talk a little bit more about the traditional side here, but bring in some new stuff to do so. So, just a little bit about our user environment design. We've really tried to take an iterative approach here, as one does, I guess. So in our procurement phase for the system, we had like a science advisory panel, give recommendations. We did user surveys. We had co-design teams craft requests for proposals, when the time came to ask for bids. And then when we got to the deployment phase, which, we've been in for a fair bit of time, delays from COVID and supply chain and all that stuff. we gather requirements for the science workflows from probably 30 to plus different user groups across the lab. And then we've been in this iterative phase since then, where we sort of prototype an integration of the environment that we want to deploy, as well as what the vendor is providing us. Then we iterate that on Gust, the test system, by debugging major benchmark and science codes, and then deploy and repeat. So the current methods, and when I say current, I'm talking about on our production system, so on Cheyenne and on Casper, it's very homegrown. So most of the software is compiled from source. We just use handmade bash install scripts. I feel like I've probably written most of them. So if this looks a little laborious, I guess that's my fault partly. But all the software is accessed on the command line via environment modules, Lua modules for us. And then we've really, on the analysis side, we've moved into fully embracing, like the Jupyter Conda sort of way of doing things. And that can be tricky to integrate for anybody who's had to do that, because Conda sort of has this assumption of I'm going to be a mini operating system and not worry about integrating too much with what you're doing from like a build from source perspective. Whereas, all of our traditional modules are being built pretty much from source with a couple of binary installs. And that's just an example right there of one of the build scripts. So what we want to do is we want to provide a familiar module environment, but we want to build it in a more rigorous way. So, years ago, we took a look at easy build. We didn't end up adopting it, but more recently, we took a look at SPAC and we are adopting it. It's been a learning experience, but I think overall really positive. So when we did those user surveys, way back when, of people running on Cheyenne and on Casper, they said that they valued our current approach to deploying the modules and doing our analysis software. But on our end, we saw that like the increasing diversity of applications and the speed of library development, especially if you look at something like NVIDIA, where they've got all new coup whatever stuff coming out like every month. It's hard to keep pace for a pretty limited team and provide the capabilities that people want, and people want to try out. The other issue is that portability and compatibility, that sort of motivates a standardized approach as well. That's obviously a big driver behind containers. But also, if we just want to build stuff bare metal on source, optimizing for the right architecture gets trickier and trickier the more heterogeneous of a system you have. And since we're going to be having a mix of Intel chips in one place and AMD chips in another place, and then NVIDIA accelerators of different generations across the enterprise, like it kind of gets tricky trying to compute something that won't give you like an architecture instruction error, if you run it in the wrong spot. Obviously, again, containers can help a lot with that. But SPAC helps us too. So, heard plenty about SPAC. Sounds like most people in the room have used it, but, just to make sure, it's an HPC package manager. It prioritizes source builds, although, there is sort of this binary cache online now that you can use. And, it also does module generation in a kind of a systematized way, which is really nice. Again, it handles that architecture optimization for us. We have to pay attention to exactly what it's going to do. And you have to give it a little bit of help, but not a whole lot. And the nice thing is it provides like thousands of ready-made software installation recipes. So, I don't know how many bash build scripts I wrote that were very similar, but now I don't really have to do that too much anymore, which is great. And also, a problem with our old approach is it became very not non-distributed. So, I got into a good workflow, but the other people on my team, it would take them a lot of time to kind of spin up on building a package using what I was using. So I feel like with SPAC and with all the documentation online, especially, hopefully we'll be able to distribute the workload across our team more, and also bring in some other people to contribute to our software stack too, which I'll show in a bit. So again, just digging into SPAC a little bit more for anybody who's not familiar, you'll build software, you'll use YAML config files. So there's a bunch of different configuration files with key value settings. So you can give like install paths. You can define compilers from a set of known compilers. Give package build preferences or requirements now, which is nice.
external packages you can specify to use, and that does sort of simplify things for Stack a little bit. Again, you can customize how you want it to do module file generation. You can also eschew modules entirely and use Stack in more of a put everything into a particular, almost like an operating system user local kind of setup. And then, specify custom recipes for, or custom repositories for package recipes and lists of installed packages. So there's a lot you can specify in these config files, and that's really the heart of the Stack user experience. This is a big wall of text, but hopefully the colors make it nicer. So, the Stack then translates a spec or a package specification into a dependency chain. I use the spec command religiously. I think it's great, especially when you give it some options to tell you what it's already installed and exactly how it's going to concretize the package. But so, for example, here's something that we install probably more than anything else, which is netcdf, and the list of dependencies that I don't need to think as much about as I did before. Obviously, I still want to make sure that it's using the package dependencies that I expect it to use. But this is a very featureful and powerful view. So using Spack, that's kind of I guess the front end user, but the back end side is what our end users see, which is just a module tree, which is going to look fairly similar to what they've seen on our old systems, and that's been our goal. So using Spack, one of the nice things that we can do a lot easier now than we could do with the old approach is to deploy versions of our software stack, and this is something I've seen other sites use and thought it was a great idea. So here, we sort of define our top level module as an ncar env module, which really just is the gateway to the rest of our module tree. So it's easy to deploy new versions of the entire tree. For example, right now on our test system, we have I guess a 2023 April module stack. And this has really proven crucial because, well, for a few reasons. One, there's trial and error when you're learning Spack, and you'll get great ideas and then they won't pan out, and you'll find out that you can't get it to concretize packages the way you want to anymore. So especially on a test system, just being able to deploy a new stack with some changes and then have it redo everything that you want and generate the same stack, but on the back end, there are differences that you're aware of, is really nice. There's been a same trial and error experience with all the Cray software that we have to integrate into the system, which has been pretty tricky to do. And then also just the pace of development for Spack itself is pretty rapid. There's tons and tons of contributors. It's a great community. But there'll be things that come online that you say, oh, I wish I had that a year ago, and you want to bring it in to what you're doing in production. So kind of just deploying a whole new version of the stack is a nice clean way to do that for the end users. But while Spack is a big step up over our old process, there's still, I would say, limitations in a process perspective. So user-specific settings can leak into your curated stack. So if you have like Conda initialized, Spack could pick up on compilers if you're not careful from Conda, and you don't want to do that. And then if you're really not careful, it might use them when you're trying to build a package. So you want to pay attention. That's why I like that spec command. And subtle differences in Spack usage can lead to different outcomes in the concretization of package. So you can get a different hash, and then Spack considers it an entire different package and might concretize your entire software stack differently. There's no really inherent way to track changes and installers either. So and I mean that from the software stack perspective. So when you install something new in Spack, I would say it doesn't quite have the nice kind of history summary that a Conda meta file has. But you can obviously track that yourself, and that's what we do. So like a lot of other sites, I think we've sort of spun up a systematized workflow here with some scripting around Spack. And ours is shell scripting, not Python scripting. So I really like what the Spack manager is doing, and that getting integrated into the Spack development when it's ready. But our workflow, so basically, we'll deploy a custom Spack fork, then we'll install packages into so we have a two environment approach. And Spack, for those who are aware, has an environment concept where you kind of put everything into a single YAML file, and it's kind of self-contained. And you can have multiple different environments you switch between from a single Spack clone. So it's somewhat similar to an environment concept in Python. But here we have two environments. We have a build environment and a public environment. So first we install packages into that build environment. We can validate the installs, test them out, test the modules, and then we can basically put them into a binary format in a build cache, and then take that cache version and install it into the public environment. Just as a note, this having two different environments does expose to us very often when there's a concretization problem. Like if something isn't defined strictly enough, it could concretize to a different hash in the public environment, and then it will try to rebuild from source instead of taking our cache version. And that's it's actually been a good check to make sure that we're defining things concretely enough for Spec to be able to reproduce effectively. And then after we install into the public environment, then we'll post-process our modules. We'll add some stuff from the Cray side of things into our final module tree. And then we also, in the scripting, will publish the changes to a GitHub repo. So just a bit more about kind of the stages here in the scripts we have. So we have this overall deploy script in our collection. This is the kind of the starting point. So it clones Spec, it configures the build environment, and then it will install an initial collection of packages from a list that we define. Then there's, I guess, that installation process happens from this install packages script. So this kind of scans for new specs that are given in a config file, which is just a text file, really. And then it installs it for all the listed compilers and MPIs. So Spec does have this concept of a stack, when you can use stacks in Spec to sort of do permutations of a single package for different compilers and MPIs. The problem I find with that is that it also defines the state of the environment, whereas we want to sort of have something that gives our intention for new builds rather than the state of the current environment. And there are reasons for that, but that's why we sort of reproduce that mechanism, I suppose, instead of using the stacks for those who are familiar. And then we'll have this populate build cache script. This is really something that they document as something you might write. And you can iterate through all the different packages you have and populate a build cache. Another approach would be to use an E4S build cache, for example, and use their packages. But again, you need to make sure you're concretizing in the same way. And then we have this post-process script where we add non-spec utilities. We'll add modules from the Cray software to the view. We have to edit those Cray modules a little bit to make them fit into how we want the environment to look, which is a tricky process. A lot of trial and error there, but I think we've gotten to a place where it works pretty well. And then we have this publish script, which basically makes sure that everything that happens in the build environment happens exactly identically in the public environment. And then we track changes and track which of our user support consultants has actually made these changes via Git. One thing that we make sure to start off with is any task begins with a shell sanitization step. This isn't strictly required, but I found it makes things a lot more reproducible. So we just have this clean bash script, which starts a new very clean bash shell. It'll only propagate very specific environment variables forward. It also starts up the particular Spec clone that we want to use and sets that up in the environment. And it also sets this very important environment variable, Spec disable local config. And this tells Spec not to use sort of your home directory config files to write new settings. The reason why that's important is if you have two different Spec clones that may be focused on two different systems, you probably don't want to use the same compiler definitions across both. There's other ways to control for that, but just find this to be very nice for shared installations. That didn't exist when I started using Spec. So I think this sort of sanitization step is less critical now than it was, 3 years ago, but we kept it along because it works for us. We found that the build environment allows for very easy prototyping, which is really nice. So every step of producing our public software stack for the users can be done first in our build environment. Both of the software stacks are entirely self-contained with their own module stacks and LMOD installs and initialization scripts. So that allows us to have this little use modules helper script. And if you run that, then you can switch from the public stack to the build stack of modules in one command. So we don't have to do a module use and manually clean the environment of all the old modules. This script just sort of does it for us, which is, handy. Our publishing process is very standardized as well. And really this is all coming down to, maybe it's just I'm not trusting enough, but I feel like when you have a team of people who need to deploy something in pretty much exactly the same way each time, I mean, I don't even trust myself to do it exactly the same way each time. So that's what this script is for. And what it does is, basically I'm checking user privileges for the public stack, make sure it's like somebody who has access to it or should have access to it that's actually running these commands. Check for unexpected changes in the software stack. So that just does like a Git comparison with what's online. We add new packages to our build cache. We swap settings from the old, like from the last commit to the current changes. We'll install packages to sync up the build in the public environments. We'll update the public modules and the like init scripts that run when you start a new shell to set up the modules. Make our YAML settings user accessible. And that's something that I'll get into a bit in the next slide. And then commit the changes and publish to GitHub. So again, it's really just trying to avoid error-prone manual duplication of work. Oops, went backwards. So the nice thing about putting it all on GitHub is users can track the changes and submit issues to the public repo, which before, they would just submit a help ticket and we could look on the back end what changes have been done. But like now, they can just look on the list of commits and see exactly what's going on in terms of new packages and new settings. And obviously can post issues as well. Get nice feedback like, oh, Go doesn't work, fix that. So yeah, that's been a nice way to go. So something that we're working on right now, we're actually testing it, and I think it will be really cool. I don't know how used it will be, but we're trying to make it very easy for users to augment our module tree with their own install of Spack. And Spack has this functionality called upstreams. It's somewhat limited, but it does work well, I think, for this use case. So basically, we have a script that we're working on where a user can run it. It will clone Spack and it will import all of our settings from our upstream instance of Spack. And what that allows Spack to do is then use all of our packages as dependencies for anything they want to build. So let's say we have like an install of I don't know, OpenMPI or something. And they want to make a user wants to do a debug build of OpenMPI and run with that so they can try to track down some error that they're running into. Well, maybe we don't want to put a debug build in our production stack, and I don't really want to deploy like a hidden module or something. They could do this and then just run a Spack install command, generate the modules, and with some of the logic we've put into the files, the modules that they generate should show up in their view of our module tree. So that would look like this. Here's an example with parallel IO. But this is like on the end user side. And basically now, if I'm the user, I can see that if I look for parallel IO, there's our version, which we provide to everybody, which is this default 2510. But then there's this debug version as well. And we've added a little like user generated module annotation in LMOD. So they can quickly see that, okay, well, this is my module, not something that's coming from the default stack. But otherwise it kind of works natively, just like any other module that we provide people. So I think that's pretty cool. And I'll be curious to see, if we can get much uptake on that. Another thing that we're sort of prototyping right now is trying to allow users to basically create a container based on the list of modules that they have loaded at a particular time. So we don't want to make like a big, we don't want to make an empty container. We also don't want to make a big monolithic container with our entire software stack. Neither of these are great approaches. But there's probably one set of software that they've loaded a set of modules for and maybe saved it and loaded every time they sign in. And like, oh, I'd like to run this somewhere else on a different system and get hopefully similar results, maybe in the cloud. We're trying to use Spack to do this. And basically what a user would do is load a set of modules and then run a command to produce a container build recipe. Maybe we provide them with a place to build that container too, or maybe they do it on a local machine or a virtual machine or something like that. But basically what it would do is you'd get a OpenSUSE image. So, our operating system designed to match through HO. It would install the RPMs needed for Spack, and it would clone our fork of Spack. And then it would add the YAML configuration file so that SPAC would operate and concretize packages the way we expect. And then get the hashes that are currently in the environment based on the modules, because these are all basically stored in the module files, so we can just extract it right out. And then you can build that container and hopefully get the same exact environment you are getting bare metal, minus some things. For example, vendor software, that's a challenge, of course. And it's still TBD. We've been talking with HPE for, I don't know, 2 years on this problem. So it's a question of like, what can we include? And then also what makes sense to include. Like you may not want to include their version of, libfabric if it supports Slingshot and your Slingshot interconnect, you're going to run on InfiniBand instead. Things like that. So we're trying to figure that out, but this is something we've heard from our users they would like to be able to do is sort of run a containerized version of our environment on other systems, maybe like a divisional cluster, maybe even a remote machine entirely. So there's been many challenges and many iterations. Consistent concretization, I think I've mentioned multiple times, has been a challenge. In particular, the Milan architecture specification is incompatible with like the system compiler, the GCC7. It doesn't have a Zen 3 architecture specification. So when SPAC tries to do that, if we ask it to, it's going to have to go back to a Zen 1 architecture, which is the newest one that it supports. And this creates all sorts of like inconsistent concretization in my experience. So now we've sort of simplified that and do a least common denominator. Avoiding rebuilds of basic packages, that was kind of tricky a couple of years ago. And for a while we had like a ton of packages being used as externals built with like GCC so that they wouldn't get built with NVIDIA and Intel and all that stuff. We don't really need all those copies of Perl, for example. Now it's a lot easier to do that without having to rely on a lot of externals because there's this require statement. So I can require it to build with the system compiler, which is excellent. I was so happy when they put that in. Simplifying the Cray modules has been tricky. That's trial and error. And we do discard, like basically, if anybody's used the Cray environment, there's the programming environments and it loads, when you load a programming environment, it loads like 12 other modules to make various things work. We wanted to simplify that down to maybe like a set of 3 or 4. But that's been a process of trial and error to find what settings from those extraneous modules that we need to keep. And then some experiments that didn't work, and this is where that iteration was handy. Using a newer GCC than the system compiler, that caused us some runtime crashes with a couple of Cray libraries. So we tried using a newer GCC as the base compiler to support the Milan architecture, but we had to bump back to the system one, unfortunately, to get things to stop crashing. And then SPAC has this bind linking mode where you can, basically directly point shared libraries towards their dependent libraries, which would greatly speed up startup of an application, especially if you're spanning like tons of nodes across a big system. But we found with some NVIDIA and Cray packages that would cause runtime crashes as well, because it kind of relies on a lot of linker tricks. There's probably ways to solve these things, especially if we get engagement on the vendor side, but for our purposes of expediency and just trying to get users running, we backed those out for now. And that's where having the versioning was very good again. So looks like there's, 3 minutes. So I'm in time. Thanks for your attention. And hopefully some of you will get to use this stuff on Derecho soon. And happy to take any questions.
Thank you, Brian. Go ahead.
I have a bunch of thoughts, but I'm just going to do one specific thought. And it looks like you've been using require, but that means that the so when they introduced require, the old preferences used to be requirements. And now they're preferences. So I'm curious if you do the production stack with release mode, like built-in release mode, or because SPAC defaults to rel with debinfo for CMake packages. And right now there's a gap in between generating all of the applications within release mode, because now the preferences, SPAC will gladly ignore what our preference is now, and it will concretize random things to rel with debinfo. So I haven't found a good way to do that. So I'm curious if you run into that.
No, I haven't found a good way to do that yet either. I haven't really navigated that.
Because you can't do
transition too
require
much.
build underscore type equals
Right.
release because not everything's a CMake package.
Exactly.
So yeah, there's just a gap there.
Yeah, I think if there, because it does seem like for certain, like I could say like for a package variant or like a package built with a certain compiler, use this require statement. I feel like they need that similarly for like a build system. But no, I haven't found a good way to do
Yeah,
that.
I guess the only thing I've done is just go into spec and then change its default because it's right. And there's like a whole issue about that. They might change it to release. And the other comment I would make is it seems like Cray's programming environment was pretty useful back in the day when we didn't have all this stuff. But now I think it just kind of gets in the way of all the stuff we're doing these days, right? It feels like Cray should just simplify all that and just let you.
Agree. Yeah, agreed. We've given that feedback, and I think it's understood by some there. And they, to be fair, like I do think that they are slowly moving in the direction of normalizing towards like what a Linux system would look like, but it's slow.
All right, thanks.
Thank you.
Thank you. I think, okay, a quick question. Okay.
What is your purge policy for the various packages? Like just say you got a new version of GCC and you guys and got overwhelming number of new packages. So do you discard the old packages or?
Yeah, so very short answer, we've sort of just kept things forever on Cheyenne and Casper. I think with this versioned approach on derecho, we'll be able to more clearly indicate to users when something has been deprecated. So I think we'll have a more rigorous purge policy moving forward, but it's still going to be, I think, lax enough to support a lot of old model builds and things like that. Thanks.
Okay, let's thank Brian again. And next up is our last presentation in the morning session. The presenter is Patrick Stegmann from the Joint Center for Satellite Data Assimilation. The title of the talk is a Fortran neural network class in a weekend. Take it away, Patrick.
Yeah, thanks for the introduction and good morning. So I'm just a little bit about myself. To begin with, I'm in the core team of the CRTM community radiative transfer model here with Dr. Benjamin Johnson. And my talk today will be about writing a Fortran neural network class in a weekend. And the asterisk here is really a 72-hour weekend. So yeah. And yeah, this work was actually inspired by the European Emphasis project, which is a neural network approach to speed up radiative transfer forward operators for satellite data assimilation. So that is the context. Now for the structure of the talk, first I will talk about the goal of this work and then why Fortran was chosen for this little project, and then why should we build a neural network from scratch, and then I will go into the technical details regarding the build system, the overall network structure, and then more detailed functions like the forward pass, the minimization routine, the back propagation for the gradients, and lastly, an application. So first off, for the goal, basically, the intention of this project is just first to create a simple, dense neural network class in a current Fortran standard with the following features. So we want to have a forward pass, so we can actually compute something, and the back propagation to train the neural network. And the neural network should have an arbitrary number of hidden layers. And we should be able to select among a choice of multiple activation functions. And of course, for the training, we also need the gradient descent. And what is not very relevant for this talk here, but more relevant for the actual operational usage is just to have an etcd4 interface for storing coefficient data and HDF5 to import TensorFlow coefficients, so networks that were trained in TensorFlow. And then going on, why was Fortran chosen here? And there are actually a number of advantages and disadvantages towards this choice. Going to the advantages first, it's a fast and compiled language, and it has a great support for arrays for linear algebra. So I think in my personal experience, Fortran is just among the best languages to use or to compute anything that has to do with vectors and matrices. And there are many legacy libraries available and also current libraries in development for Fortran due to its long development history. And it has good support for parallel programming, not only with OpenMP and MPI, but also the new co-array features and things like OpenACC for accelerators, etc. Then it's also widely supported on HPC infrastructure. So if you log on to a cluster, then usually you have a C, C++, and a Fortran compiler already available. And lastly, the most important aspect here, or it's maybe not necessarily an advantage, but our users actually requested having a Fortran program available, so they're comfortable with using Fortran. But then now going on to the disadvantages, it basically has poor support for all kinds of data structures except arrays. And yeah, that really makes it difficult to develop more complex computational operations that involve more complex data structures. It has poor generic programming support at the moment. As far as I know, that is supposed to change in the future. But something like templates and C++, for example, are not available in Fortran. And so that has a number of disadvantages, and especially for deep learning applications, this also makes it difficult to use automatic differentiation features. Then furthermore, the object-oriented programming support is relatively poor. So it is available, but it's a bit clunky. And so that makes it a little bit difficult to express certain ideas. And it also has lots of boilerplate syntax, or at least more boilerplate syntax than other languages like Python or Ruby, for example. Then the next question is why build a neural network from scratch if you have TensorFlow and Keras and all these other nice libraries already available? And here I would like to start with a quote from Richard Feynman, who is attributed to say, what I cannot create, I do not understand. So with the increasing importance of machine learning applications, especially the large language models, for example, it's really important to have an idea what is actually going on under the hood with all these models. And then furthermore, if you implement this yourself, there are also many concepts in the implementation of these neural networks that are important and translate well into other areas like adjoint programming and automatic differentiation in data assimilation. And then, as I've mentioned before, with our users and our community developers in the CRTM community project, the infrastructure support for Fortran is easy, and the developers are well familiar with using and programming Fortran. And so it was requested to have a Fortran interface. And it's kind of difficult to get a good Fortran implementation of a neural network at the moment. So moving on to the technical details, the first choice we have to make is what kind of build system we want to use. And in our current project, we are actually using EC build, which is a extension of the CMake build system that is maintained by the ECMWF. And so it was natural to just go with the base CMake version at the moment. And that was what was actually chosen here. And the reasons for that is that CMake is portable and it's easy to use, and it's straightforward to implement a clean structure for the project with your source folders, tests, and build directory. And it's also easy to include unit and regression tests. And the dependency management is facilitated. So as I mentioned before, we want to use netcdf and HDF5, for example, as APIs. And that is really straightforward with CMake. And on top of that, we also get easy or relatively easy integration between Fortran and C and C++. And on the right-hand side, you can see a little code snippet of one of the unit tests that is included in the project, where a neural network constructor is tested, basically. Then going on to the actual architecture of the network code, so for the network structure, it's fairly easy. So you can see, you probably have seen that a million times before already. So for deep learning hidden layer, fully connected neural network, basically we have here a set of multiple layers that are connected, or you can also consider it as nodes in a computational graph. And we have an input layer, one or several hidden layers, and an output layer. And the input data flows between the different layers to be processed, and it's eventually reaching the output stage. And then we also have a back propagation algorithm that gives us the gradients in order to fit the model to our training data. And so here's how this actually looks in Fortran. So I chose to implement a network container class that holds this sequence of layers or nodes. And this class declaration here actually has a number of type-bound procedures. And of course, we have our constructor and destructor that is available now in the current Fortran standards. But we also have a separate initialization procedure to initialize the weights and the biases of the model. And the forward pass and the back propagation pass are also included in the overall container structure. And at the top in the data members, you can see that we have a layer sequence of type layer where the actual layers or nodes in the computational graph are contained. And of course, in Fortran, this is implemented as an allocatable array. Now, for the individual layer and node classes, basically, you can see the layer class implementation here as well. And it does contain the weight matrices and the bias vector for a single layer. And the activation function is a type-bound procedure here as well. And what is done here is simply, in order to select a different activation function, you pass the name to the activation function procedure, and then this procedure selects the different types of activation function automatically for you. And then the outputs of the different layers are also stored as a vector for the backpropagation stage. And you can also see that I was trying to play around with storing the activation function as a procedure pointer, but that didn't work at the moment. Now for the forward pass, this is the actual computation of the neural network output, and this is just a recursive function application for each layer, and it basically consists of two stages. So you have the first, you have the input vector, which is coming from either the direct input or from from the output of the previous layer. And that input vector first undergoes a linear transformation. So you have the weight matrix multiplied to the input vector and the bias vector added to that. And then this outcome is used in a nonlinear mapping in order to get a nonlinearity into our model. And this is recursively applied to the multiple layer stages in the model. Now for the implementation, this is actually quite straightforward, as you can imagine. So we just have a type-bound procedure here with all these inputs, and it's part of the neural net container class. So it's not part of the individual layer, but this is something that might change in the future. So we can better emphasize that a recursive character of that function application. Then moving on to the minimization procedure. So this is relevant for the training of the neural network. So if we have some training data and we want to apply the neural network to that training data. And here's just some pseudocode to explain how this actually works. And for this algorithm here, we start by initializing our network. So we need to randomly assign the values of our weight matrices and biases. Of course, there are certain restrictions that apply here as well in order to avoid vanishing or exploiting gradient problems. But I'm not going into detail there. And then we're actually going to process our training data in, or commonly the training data is processed in terms of batches. So you don't process your entire training data at once, especially if you have very large training data sets, but you split it into batch training sizes. And for each batch, you set your cost function to 0. So you're working with a cost function. And then inside each batch, you iterate over the training data inside the batch. And you compute, first you set the training input from your training data. And then you compute the forward pass of the neural network for these training data. And you store all the intermediate results. And then you update, you add the cost function for each training data point based on the output of the model, based on the input training data, plus the expected output available from the training data. And then you will run the gradient descent algorithm. And then for the gradient descent itself, it's very simple. It's just an approach to minimize the cost function. And you can see the connection to variational data assimilation here quite clearly. So if we have a neural net parameter theta here, which can be either the bias or a weight matrix element, and we have our iteration step k+1, then the theta value at k+1 is computed from the theta value at k plus the adjustable learning rate eta. So this is something that the user can supply, times the gradient vector of the cost function with respect to the corresponding parameter. And so the gradient descent step itself is actually quite simple. But then the computation of the cost function gradient is actually where the difficulty lies for neural networks, because you can actually do that with finite differences, but because of the large number of parameters that are commonly encountered in neural networks, this will easily become very expensive. And so what is facilitating the computation of the gradient here is actually the backpropagation algorithm that became quite famous for neural networks. So moving on to the backpropagation algorithm. This is, as you can see here, the backpropagation algorithm is basically an agile encoding approach to compute the gradient by repeated backwards application of the chain rule. And so you can see here in the formula that we want to compute the gradient of the cost function, for example, with respect to one of the weight matrix elements. And by applying the chain rule, we can basically split this up into different gradients. So at first we have the gradient of the cost function with respect to the layer output from the nonlinearity. And then we go one step deeper and multiplying it with the derivative of the layer output at the nonlinearity stage with respect to the layer output after the linear operation, and so forth. So basically you get these, because the neural network itself is just a sequence of nested function applications, the Leibniz chain rule here just leads to a sequence, a recursive sequence of the different nested functions. And in order to get the gradient of a parameter in a hidden layer of the neural network, you basically need to start from the back of the neural network and sum all the gradients of the parameters that are influenced by the current parameter in the layers that come after the current layer. So essentially you're stepping backwards. You need to step backwards through the neural network. And so here you can see the parallels towards the agile encoding approach. And yeah, then for once we put all this together, we can go to the application. And this is a quite simple application here. So we can just look at a one-dimensional function and a simple neural network with one input layer and one output layer and two hidden layers. And we can generate some random training data for a cosine function, as you can see here. So those are the blue points. And then we can use those training data to train our neural network. So basically what was done here is just taking training data points from a cosine function and adding a little bit of noise. And as you can see, after training the neural network, you get the blue curve. And despite the noise in the training data, it actually reconstructs the cosine function quite well. And yes, that is my presentation. And thank you for your attention. And I'm open for questions.
Okay, thank you, Pat. Seems like the online portal. I encourage our online audience to post any questions, and I will check for in-person audience. Please walk up to the mic.
Thanks for the walkthrough. In my experience, one of the biggest difficulties with getting neural networks to have a good API for users is composability of layers. And in that respect, TensorFlow and PyTorch are different because TensorFlow talks about layers as entities and PyTorch talks about kind of the output of each operation as an entity. Do you have thoughts on the way that you could make a generic interface in Fortran for one layer to understand what the previous layer is doing, or to have kind of a generic type of layers?
Yeah, thank you. That's actually a great question. So and what I would like to do is actually represent a machine learning model in terms of a computational graph. And so I would really start with a node in the computational graph as the basic structure. So what I've shown before with the layer. So I've named it layer in the current implementation, but it should rather be node as a more general term. And the problem here is, say if you would implement it in C or C++, for example, then you could use pointers more easily to connect the different nodes. And with Fortran, for me, that's, I mean, it's not impossible, of course, but it's a little bit clunky to implement. And so I think the biggest obstacles in implementing such an approach in Fortran is first, the relatively poor support for data structures other than arrays, and second, the lack of generic programming support similar to the extent of C++ templates. Yeah.
Thanks. We have one question from the online portal from Daniel Abdi. The question is there a Fortran backend for model trained with TensorFlow? It may be easier to train a complex model with TensorFlow and write only the interface code with C or Fortran.
Yes. Yes, the answer is yes. So we're having both the option to train the model purely in Fortran, but that is limited to the hidden layer structure that I showed before. And with TensorFlow, of course, you have more flexibility. But we do provide a HDF5 interface to load TensorFlow coefficients.
Thank you. I'll turn it back to our in-person audience. Do we have more questions? Go ahead. Yes.
Thanks. Good talk. And maybe you said this, I missed it, but I guess, are you planning to parallelize your Fortran version? And if so, what's your strategy for that, or plans for that?
Yeah, eventually. For neural networks, yeah, that parallelization is, of course, pretty favorable. And as a first approach, I would actually use OpenMP just to parallelize the existing layers. And yeah. And then further on, yeah, see if maybe OpenACC can also provide some benefits that we can access GPUs, for example.
Cool. Thanks.
And move on to the next question online from Timothy Slingwinski. The question is, since you mentioned this was partially written in Fortran for your users' benefit, have you seen your users gain a better understanding of and less apprehension towards using neural networks now with these tools versus methods that were used previously?
Yeah, that is actually also something that we're interested to gauge the level of user engagement there. But it's a brand new code that was written only recently, and we're in the stage of making it available to our users and see what they can do with it.
Thank you. And actually, from my own question, just to follow up on that, I see this, one of the benefits can really be, a kind of easy integration with, Wharf model and other community models, which is in Fortran. Is that part of the consideration during your development of this tool? Let's say making integration of a neural network in this models easier.
Yes, definitely. So this actually came out of the consideration to include it in the CRTM, in the community radiative transfer model. because we have a number of computational processes there that are that would benefit from a neural network parameterization. And so we have things like the transmittance computation, or we have a number of large lookup tables that could be represented as a neural network instead. And so that is also a major reason to implement this in Fortran, so we can directly use it in existing models. But it's also available as a standalone library of sorts, thanks to the CMake build system. Yeah.
Thank you. And I think that's it for questions. Final check in person. Okay, let's give another round of applause to our presenter, Tariq Stegmann. Thank you.
Thanks.
And with that, we have concluded our morning session, and we can move on to our schedule for lunch. Online audience, please take the time to get charged up. We'll reconvene in an hour.
Okay, sounds like everyone can hear me. I'm assuming you can. Let's go ahead and get started with our last section of speakers. And just FYI, after these next two speakers, there'll be a break, and then we're going to come back in here for a short discussion. And then after that, it's, social time. So yeah, if we can go ahead, we have Julia Kent, who's presenting on how Project Pythia leverages GitHub for community contributions. See, so, yeah.
Hello? Yep. Okay, great. I'm Julia Kent. I work here at NCAR on the GeoCat and Project Pythia teams. And I'm going to talk to you today about Project Pythia, how we exist as a community element, an open source project, and how we use GitHub to bolster this mission. Now, I'm not a GitHub ambassador, and they are not paying me to be here or anything like that. I'm also not an expert. Like yesterday, some of our actions were failing, and I was going to go fix them right after this talk, ironically, but a colleague fixed them, so hopefully I still understand them at the end. But I'm trying to I know this is a mixed audience of different people with different familiarity with open source practices, with GitHub, trying to incorporate some of this into their work. And I'm going to position myself as someone at NCAR who you can come to if you need help figuring out the options you have available to you or debugging what's happening in your GitHub actions. Is this? Okay. So first, thank you to everyone on the Project Pythia team. We've had a lot of people contribute over the couple years that this project has been ongoing. This is open source, as I said, so if you want to help out next time, I give a similar talk, your face will also be on the slide, and hopefully that's motivation. So first, I'll give an overview of Project Pythia. We're trying to address a couple main challenges in scientific computing in Python. One of them being that there are just so many packages out there that can be very overwhelming if you don't know exactly what is best for the job. You don't know how different packages interact, what's stable, what's trustworthy. And so here we have an image of the Pangeo stack. So these are packages that members of the Pangeo community have identified as being either like so widely used in geoscientists or maintained or developed or built specifically for geoscientists. So Project Pythia tries to provide learning material to bring everyone up to speed on the necessary packages they might need to contribute to the Python geoscience ecosystem. And also shows demonstrations of how to use different packages in conjunction with each other. Another challenge that everyone in this room, I'm sure, is aware of is just the huge size of data that we're talking about. And we want people to do their computation wherever the data is, so they're not shuffling and saving and duplicating and all sorts of stuff. So may that be on an HPC system or the cloud. The struggle with this is that cloud computing is great, but it is also still a new emerging technology trend. So there's not that much consistency in what the user experience might look like, which is also overwhelming, another hurdle that is stopping some people from contributing. So we provide different cloud environments where people can practice pointing to data and playing around with different workers and things like that, so that more scientists can train in doing their analysis in the way that is more computationally efficient. And to this end, we have Project Pythia. So again, we are geoscience focused, a collection of tutorials, videos, courses, things like that, that can bring people from not knowing any Python at all to being able to contribute to this community. And we are the education working group of Pangeo. So that comes with some responsibilities, such as training people on the cloud and HPC, training them on Python packages, on analysis or software best practices, both having strong documentation and documentation on how to have strong documentation for the packages that you build. And we're trying to build this community so that more scientists can help each other speed up the coding step of their scientific process by sharing experience and creating templates that we can kind of reuse for slightly different applications and move forward. So the first thing you see when you come to our site is the portal. This is our homepage. From here, you can navigate to our other learning resources, which I'll have a bit more to say than this one. So first off, we have our resource gallery. This is an aggregation of resources from across the web that we have found useful for someone trying to learn. There's probably at least 50 different resources in here that we found. And you can submit a resource, submit documentation to your project. Let us know if you found something useful that's not here. Something that is really great about this is it's filterable. So if you're looking for a specific affiliation or domain, say you only want to see examples with your specific field within earth science, you can search for that. And also formats, say you'd rather sit back and watch a video or engage in an active tutorial. And you can filter by packages. So if you're doing a deep dive on learning how to use NumPy or learning how to use Dask, here's a collection for you. We also have a foundations book. So this is a free online textbook. Yeah, all the other resources that I mentioned, we only advertise free resources. We will not host anything that's behind a paywall. So our foundations book has chapters on every package that we think is necessary for someone to have a core understanding of Python computing to move forward in the community and working in community. A little bit more advanced, we have cookbooks. So these are really exciting because they are a little bit more niche or more advanced, or they combine different tools. Basically, great workflows that are common enough that it's worth sharing, demonstrating, and somebody can learn from it and apply it to their own work, but not so universally applicable that we think every single person needs to know how to calculate radar data on AWS, things like that. Again, these are also filterable by domain and package. And each one of these has a Binder Hub instance, so you can play with the code on the cloud and test your understanding there. I'll talk about this a little bit more at the end, but this summer we are having an event, a hackathon on cookbooks that we're calling the Cook-Off in June, and it'll be at the Mesa Lab. And so I would love to see anyone in this room come and bring the scientific software that you've developed and leverage our existing audience of the Pangeo community to bring that resource to people to see how it works in action with data on the cloud. So I'm going to kind of just quickly run through what one of these cookbooks might look like. So there's also going to be a lot of markdown, leveraging Jupyter to have explanations and equations and things like that. And each Jupyter notebook within a cookbook is kind of like its own recipe. And so this will just be kind of like what a typical one might look like to give you a taste so that you know that this is something you'd be capable of contributing to. So typically, you start with your imports. Then you have, as I think the first talk of today was talking about the challenge of searching for and selecting the data that you want. So this cookbook uses a rather large if, for loops, while loops, all of that to kind of condense the data on the server to get the actual data that we are looking for. Some cookbooks use intake or intake ESM, some other options. Then you'll see opening the data, taking a first look at it. Here, the data is lazily opened as an opened app endpoint. And we just kind of take a look at it to make sure everything is good. And then you have your data cleaning, processing, and computing. So typically there might be some regridding or something going on. Here we weight by area and compute global average surface air temperature. And the final hurrah usually is some sort of pretty plot that feels like you've accomplished something, maybe accomplished something that if you plugged in your data, changed the function a little bit, it would produce something that might be publication ready, perhaps. So again, we're kind of trying to hone in on what could be an analysis pattern for scientists here to move forward together and add to this experience reshare. So we are a community tool, and that means we have to be open source. We have to engage with people, make sure we're listening. And here are some practices that help us to that end. So we actually have a couple contributors guides for different niche ways that someone might want to get involved. There's different levels of involvement. Maybe you just don't like the way a sentence sounds and you want to tell us, or there's a spelling mistake, something's not clear. You could also, contribute some of your own content or attend our weekly meetings to get involved in the content and infrastructure ongoing decision-making process. So we also have people attend our meetings to work on collaboration. So one collaborator we're working with right now is Climate Match Academy. That is a summer school, like 2 weeks for undergrads all over the world to try and bring climate science education to underserved or underheard communities that, their voices aren't as loud in the climate conversation, even though they're equally or more affected by climate change. So they're going to be leveraging Pythia content for all of their Python learning, which is great. We don't have to keep reinventing and reinventing how to learn stuff. And so we've had a couple people come to us and ask us for some Python support as they want to use Pythia as the foundation that they build the rest of their tutorials off of. We're also active on Twitter and a Pangeo discourse page if you'd like to join a conversation there. And as I said, we had weekly meetings. We had one yesterday, so I'll see you on Monday if you want to come. Okay, so we leverage GitHub to help make some of this possible, to lower the barrier of entry of the infrastructure needed for someone to contribute to our project. So we've done a lot of automation, and that's kind of what I'm going to share with you today, some of the decisions that we made. This isn't a tutorial on how to do the automation. It's kind of an overview of some of the things we use. So everything is on GitHub. We have 27 different repositories within our own organization. This works for us, again, because what we're building is a website product. And so different components of the site might even have their own repository. But every single cookbook has its own repository because it needs its own environment file for its own binder on the cloud instance. Otherwise, it would get so bloated if we had every single package that all of our content needed. We recently started using the GitHub project board. I think before things were different, kind of scattered, or it was hard to have multiple repositories in the same place. But now we can actually have all 27 of our repositories in this one image that we can kind of filter by different things. So it's a really great way of checking if any issues from this one repository no one's touched in a couple months, like let's go revisit that. This really helps us see. And GitHub Actions this is the area that probably has the most potential for you, but also the most potential for headache and heartache. So we use a lot of different actions. You might use them in your continuous integration workflows to make sure that tests are passing before you merge. We also make our sites rebuild every single night, build after a pull request is merged. We have previews so that you can view what a pull request is going to do to the site before it's merged and things like that. And it goes on, and we have actions like this to make sure that our cookbooks are still continuously runnable, which makes it different from some other galleries you might find on the web. Is this like maintenance piece to it, to making sure that as environments change, as environments update, the content we're providing is still stable. So of course you have to go in the settings to make some of this work. You have to let actions run, maybe let them run on forks. There's some secrets involved, which I can't tell you about, that you might want to share with third-party apps. That can be a little bit confusing the first couple times, and make sure you put branch protections in place, things like that. Another setting that is very common is to enforce that all checks have passed before anybody merges anything. So that's a good thing to do. It lowers the barrier of it lowers like the load of work on any one person who wants to help with the project. They don't have to worry about missing this huge failure that's gonna break everything. Okay, so hopefully this is big enough font. I just thought I would show you one of our YAML files for one of our actions. So here we basically, whenever there's a pull request, it will trigger this book build so that you can preview what it's going to look like before we merge it. And it'll kind of it'll create the book, zip it, host it on a different site. We use Netlify. And then go back and it'll post a comment with a link to the build. And this is what that looks like. So this was a time I was just playing around with adding icons to our gallery or to our portal page for the different sections that we offer. I think in the end, I didn't really like the icon that I could find for resource gallery. So we're not doing this, but it was nice to be able to see what it was going to look like first. And even though I can build it locally on my own machine, for someone else to have to go and like make a copy of my pull request, create the environment, build it, open it in their browser, there's a couple steps there that we can lose people along the way. And this is just one click and is so seamless, and I really appreciate it. Okay, so like I said, I want to kind of leverage myself here as someone you can come to if you want to have any similar workflows work for you and your project. So the Earth System Data Science community has office hours. You can get to that from this QR code or the ESGS blog, and just choose an appointment with Julia Kay, that's me, and we can kind of talk about your project, what might work for you. Because again, like anything open source, GitHub Actions, there's so many options across the web that it can be hard to sort through. And again, this summer, we're having our cookbook cook-off. So that's June 21st to 23rd. It'll be in the Mesa Lab and virtual. It's free to attend. We do have a hotel block, all sorts of stuff, if I can try and convince you to come and bring your tools again. And with that, thank you. I'd like to thank the NSF EarthCube program, the award that funds this project, the Pangeo community, all the technical staff that's worked on it, and the ISS Conference Committee for making this possible. Thank you.
Great. Oops, sorry. Thanks, Julia. First, are there any questions in the room? And I'll also check online real quick.
For the overview of all the stuff that you're doing with GitHub, that was really nice. You made a quick nod in your intro to it being annoying to debug GitHub Actions workflows. I would assume that means that you don't have any fun tricks for how to do that without emailing your entire GitHub owners list every single time you fail.
I think my fun trick with that would be for everyone on the GitHub owners to change their email settings.
Okay, well.
But there are also ways by setting up a Docker image on your own machine that you can recreate. You follow the YAML steps to recreate the GitHub action instead of having all of that happen once you push. Because I know like our nightly builds, it's not working. I'll try again tomorrow. Every single day, that can be a very long iteration.
Yeah, you might need to touch base.
Okay.
Julie, this is awesome. Really good to hear about this. On the GitHub Actions, if I got it right from your slides, there was an action that would create a plot. Is that right?
When
you were showing the icons?
Go back. I don't.
So that site preview. So that's the site preview is an action that'll produce that plot. Is that or that page? I guess. Is that what happens?
Mm-hmm. Yeah, so it'll create this comment box, the comment on the GitHub pull request, and then that links you to a version of the site that isn't live yet.
Oh, wow. Okay, that's really cool.
Mm-hmm.
Okay, thank you. Awesome.
Thank you.
Thanks, Julie. It's a real quick question. You had mentioned the project board being super useful with the 27 repositories. That makes total sense, but I'm just curious, like before you were using that, how did you keep track, or did things just fall by the wayside?
Mm-hmm. Mm-hmm. Well, we've definitely shuffled things around at different points during the life cycle of this project. I think at one point when I first started at NCARG, we actually built our own project board with actions that would pull from the repositories that we were interested in. And then, well, that's not necessary anymore, which is great. During our weekly meeting, someone is in charge of making the agenda, and normally if there's time for it, and one of the items would be to kind of go through all of the issues on, I think we would have two like main repositories that most of the infrastructure and content work is happening on, being the portal itself, which is now in a pretty stable state, and then the foundations book that we were actively iterating on improving the content. So there was a lot of stuff happening in those two main places. Since then, moving on to the cookbooks, that's when the number of repositories has really exploded. And a lot of the infrastructure along those different repositories is the same as each other. And so we're actually investigating a way for GitHub to automate if I change our like template repository, it to change everything that inherited from it. So some of those issues on a specific cookbook repository are relevant to the authors that are actively involved in it. Not everybody on the team needs to always be checking in on the issues that are happening, but it's good that now everything is more transparent.
Maybe just a follow-up then. So are there any capabilities that you had in the sort of homespun setup before that you haven't been able to replicate or offload to, kind of the native GitHub project management?
That's a good question. I think one thing that maybe we had done was, this was when my team was kind of working on various tasks across Pangeo. So not everything was owned by the same organization. So we would have to like borrow this from X-Ray, this from NCAR, and want those to appear on the same project board. I'm not sure if GitHub can let us do that, but we've moved all of the Pythia repositories into our Pythia organization.
Any other questions? We still have about 6 minutes. And there's none online. Okay, well then I want to ask one. So do you do any testing through GitHub Actions of kind of the notebooks themselves? Like make sure that they still, run and produce plots, and if so, how do you do that?
Well, so we have our notebooks they are run at the build time. So the version that's saved on GitHub does not have all of the output cells in place. And so at build, if a notebook fails, the build fails. So that does work for us. But we do have things in place if you want a cell to break to demonstrate why you don't want to do something a different way. That's, we've done that, but it's a step harder.
So just so I understand, so if during the build phase, it'll run through like the notebook just to make sure that it runs. But then when the final file that's submitted to GitHub doesn't have those cells filled.
Yep.
Okay.
Yeah, so we don't have in place the same testing suite you'd want for a computational package, making sure that the output is exactly what we'd expect the output. We don't have those tests in place yet. I don't know that that is expected out of an example workflow, but it's something worth investigating. It's something we're talking about in our conversations about like DOIs and citations of cookbooks. So you can cite different versions of them if something breaks down the line and we want to change it, things like that. So
cool, thanks.
Thank you. Do I do anything on here or no?
Nope. Okay, yeah, just waiting to see if anyone else, but yep, thank you. Okay, so I guess we're ready for our final talk. Eric Lingerfelt and Tariq J. Hamzey. Hopefully I pronounced that right. Okay, that's fair. That's yeah, here to talk to us about R2D2, which is what we want to know about.
All right, thanks a lot, guys. My name's Eric Lingerfelt, and I'm a core staff member and software engineer in the Joint Center for Satellite Data Assimilation. My role at the JCSDA is the database and user interface lead in the infrastructure group. Is that my thought?
Yeah.
Oh, there we go. Oh, okay. My name is Tariq Hamzey. I'm based in Virginia with a science and technology firm called SSAI.
And we list our other collaborators here who help us maintain not just the software, but also the data stores and the data that we have in R2D2. So we're going to do a quick walk through some of this and talk about some of the lessons learned that we've found out while we've redeveloped R2D2 over the last 7 or 8 months. So we'll talk about the introduction, how we deploy R2D2, take a look at its architecture, talk about some of the strategies that we learned while we re-implemented R2D2 from the previous version, and just highlight some of the future capabilities we hope to offer.
Okay, so my company does a lot of contract work with the federal government, and the contract that I support is with the GMAO, Global Modeling and Assimilation Office at NASA Goddard, and the GMAO in turn supports NASA's Earth observation missions. And one of the primary ways in which they do that is by building state-of-the-art data assimilation computational models. And one of the most prominent models is the GEOS suite, Goddard Earth Observation System. And this is this is kind of an umbrella for many models and experiments that are run with that engine, like analysis, forward processing, reanalysis, composition forecasting, all that fun stuff. Now, the GMAO is gearing up for a transformational shift to the infrastructure in which these models are built and operated in. So that's comes with a lot of challenges, but also some opportunities. So some of my colleagues at the GMAO are taking this opportunity to revise some of the workflow tools that are used to instantiate and run new experiments. One component of these workflows is a data service. We need a way to abstract the ingestion and output from these models. And to that end, we've been collaborating with the Joint Center to develop this database tool called R2D2.
And so we'll talk about the mission of the Joint Center for Satellite Data Assimilation. We are here to accelerate and improve the quantitative use of research and operational satellite data in weather, ocean, climate, and environmental analysis models. As you can see here with the lines of code that we currently have from many different collaborators and different codes that interact with the software that we generate. The main push of the JCSDA is a new platform called JEDI, which stands for the Joint Effort for Data Assimilation Integration. And so then basically what we want to do is work together to bring together not just observational data, but other forecasts to improve data assimilation across ocean, land, snow, sea ice, aerosols. And we have many core partners. So our core stakeholders are NOAA, NASA, the United States Navy, and the US Air Force. But we also work a lot with, of course, UCAR, the UK Met Office, NCAR, and the ECMWF. And we work in collaboration with over 35 universities, private companies, and several other international institutions. So for JEDI, our core effort is to create a unified approach for algorithm development, observation processing, but also maintenance of software. How do we exercise software engineering best practices in order to assure that we have a great product? And so one of the core missions of the Joint Effort for Data Assimilation Integration is this rapid integration of innovation and research for operations. And so we're kind of an innovation center for all of these stakeholders. So we want to very quickly develop new software tools that can be applied to data assimilation from satellite observations across all of our stakeholders. And here is just a small portion of the different satellites, platforms, and sensors that are used in the JEDI system. And so what we want to do is be able to bring all of these together and make them accessible to data assimilation scientists and weather forecasting. So, and since this is JEDI, we have a lot of acronyms that are related to Star Wars. We have R2D2, but we also have things called Ewok, Vader, Saber, and so forth. So R2D2 is basically the database for JEDI. It interacts with every single component for all of our data assimilation, high performance computing, and also cloud computing algorithms. And so, but basically what it is in this sense is R2D2 is a database wrapper. And so we're, in this case, we're wrapping MySQL for data management and registration services for the data assimilation workflows. So we apply storage, access, search, and update to these records. So one thing I want to stop here and point out is that we heard about refactoring from David Bernholtz's tutorials yesterday. And so up until last October, we were using a previous version of R2D2 that integrated with no database technology at all. We actually saved and stored files in file names and file paths that had the metadata, which is okay if you know what you're looking for. But if you're wanting to search things and be able to sync data stores and really do large scale scalable data access and management, that was no good. So we decided that we were going to do a refactor of the code, but it ended up that a refactor wasn't enough. We basically started from a blank sheet of paper, and what we're talking about R2D2 today is actually the version 2, which Tariq and I have been working on with the JEDI team for over the past 7 or 8 months. And so R2D2 is basically an intuitive Python API that integrates with MySQL. And so basically we, at any time, a user or an automated workflow, which we'll talk about in a second, says, I want this data for my experiment. And it talks through the Python API, and we have distributed, and it queries a MySQL server, and that server tells the user or the simulation where to go get the data and where also to save the data. But primarily for researchers, it got a little jumbled there. But what we want to do is make a black box. And so the data assimilation scientists and weather forecasters are completely hidden from the technical aspects of the data ingestion. Basically, we want to close the gaps between the users and the physical location of the data and manage all of this data so the data assimilation scientists and the weather forecasters don't have to worry about where to store their data or where to find their data. It's there when they need it. And so out of JEDI, we have a very rapid software release system. So we release something called Skylab. It's our flagship application every 4 months. And just earlier this week, we released version 4, which includes the new R2D2 implementation. But this flagship application incorporates atmospheric, ocean, sea ice, and soil moisture and snows into our simulations, but it completely depends on R2D2 for managing its observational model and diagnostic data. And so here on the right, we have the JCSDA Skylab data viewer where you can go and see the results of all of the latest Skylab models that we're running. And so R2D2 is also tightly integrated into the workflow system that's currently being developed at JCSDA called EWOC. So it's the Experiments and Workflows Orchestration Kit. And EWOC is also another Python wrapper, but we're wrapping around the EC Flow workflow manager from the European Center. But we're looking to also implement the Silk workflow manager at some point. And also here you see the advanced baseline imager from the GO-16 satellite brightness temperature is one of the results of Skylab. Another thing that we find very important at the JCSDA is the application of FAIR principles. And so if I jump back to this slide, so every single one of these satellite sensors, all of these outputs, they come in many different formats. It could be buffer or HDF5 or NetCDF. But what we need to do in order to convert these formats into a central reusable interoperable format, the JCSDA also has YODA, or the Interface for Observation Data Access. And so basically this front end that we use to convert all of our observational data into a central format that's expected by the Skylab application. It handles all of the observation data, and then also it stores the output of our diagnostic data, so the results of each model. And it has NetCDF4, HDF5, and ODB backends. So what are the FAIR principles? And so we have findable, accessible, interoperable, and reusable, as we saw from the talk earlier today. And so between the jointness of R2D2 and YODA fulfills these. So R2D2 allows all of our observational data to be findable and accessible. And then the YODA format itself allows us to be interoperable and reusable. And here I have a headline from Shelley Stahl. So let's talk about deployment of R2D2. So first and foremost, we have R2D2 has data stores that we mirror and we keep on multiple high performance computing centers, such as Mississippi State's Orion, the Center for Climate Simulations Discover, NASA's Discover, Cheyenne, which is managed by CISL, and also the Space and Science Engineering Center at the University of Wisconsin-Madison, which is S4. Our MySQL database server, which tracks all of this data and all of the metadata that identifies this data and makes all of this searchable, is a MySQL server in the Amazon cloud. We also have mirrors of all of our data stores in Amazon regions, US East 1 and 2, for our cloud computing that JEDI uses as well. So we can talk about what our current data holdings are. So of course, some of our data, we keep mirrors of data so we don't have to continuously pay for egress out of the Amazon cloud, but it contains a wide range of analysis, bias correction, feedback, forecast, observation, and visualization data files. And it enables, and along with R2D2, along with the JEDI and Skylab applications, enable the execution and analysis of multiple models, including GFS, GEOS, MOM6, MPAS, GFS Aero, and GeoCF. A lot of these we've heard about during our conference. But we also maintain, not only do we maintain data stores where people write their results, but we also maintain a canonical production set of input data for all of the Skylab executables. And right now, R2D2 version 2 is currently tracking over 4 million files, and we have around half of a petabyte that we have stored. And here is just some more examples of the observation data, and also H of X, O minus B, which are common quantities that you would look at in a data assimilation run. I'll let Tariq take over the second.
Okay, thank you, Eric, for that context. So now I just want to give you some basic details about the internals of the R2D2 database design. So you can think of the R2D2 database as two separate components. You have the MySQL backend, and then you have a file directory that actually stores your physical files. That's organized by MySQL and the Python wrapper. Now, we're just going to talk about the MySQL backend. Each record in this MySQL database, it has two flavors. It could either be a data item or an index item. And you can think of items here as like shopping cart items, right? They can be any record that represent either a data file or something about the metadata that we're using to describe all the users and hosts and platforms, et cetera. So here on the right side, you can see a plot that demonstrates the relationship between a data type like feedback and how it relates to metadata on the right side, an index. And we'll explain that more later. Okay, so these are all the index items we have. Index items are metadata that store information about data stores, experiments, models, hosts, observation types, users, etc. So each one of these blue labels at the top represents one table in the SQL database. And then beneath them are the column names in that table. Some of these columns are required and have no defaults. So if you're querying these data, you have to supply them. If you don't supply them, R2D2 will patiently tell you that you need to supply this information. All the index items have a name associated with them. And that is one of the key distinguishing factors between index items and data items, which I will get to next. So these are the data items. Data items represent attributes of the ingested data files. So we have right now 6 different kinds of data files. We have analysis, bias correction, feedback, forecast, media, and observation. And you'll see under most of these data types, we have models and experiment attributes. If you're querying a data file in this database, but you don't have a model or experiment registered as an index item yet, then again, R2D2 will let you know, we don't know how to interpret these data files because we don't have the metadata on record. All of the data items, as opposed to the index items, they don't have names, but they do have some sort of date parameter that indicates when they're valid. So one of the key strengths of R2D2 is that it's easily extensible. The Python code is essentially schema agnostic, but for the distinction between index and data items. The schema is dynamically loaded at runtime. So that means that when we want to add a new data type, we don't need to alter the underlying Python code at all. Nor would a new data type impact the underlying file storage system. So we can go crazy here. We can add whatever data type we want without having to touch any code at all. Another strength of the R2D2 Python API is that it's very lightweight, and I'll show you what it looks like in a moment. Functions are atomic. We feel very comfortable that the integrity of our database will not be disturbed. And in order to query our database, all you need to know are the basic key value pairs that describe the data you're looking for. Okay, so these are some of the core functions that you will use to interact with the R2D2 database. If you're familiar with SQL, you know all about CRUD, create, read, update, and delete. We don't have CRUD, we have SUI and RIGUD, which doesn't exactly roll off the tongue. But essentially, the two functions that you'll be using primarily are store and fetch. When you store a data file, you take a data file that exists anywhere in the file system, and you describe it with its attributes. You give it a label for what kind of item it is, and then it registers that data file into the R2D2 database. The same exact thing happens with fetch, just in reverse, and then you get a data file out of the R2D2 database. We also have methods to update these data, both for metadata and data files. We can erase and delete them at our discretion. And we have many different ways to search for data in the database. We can search them by name, or we can search them by an index. I mentioned how data and index items are subclasses of an item superclass. And the methods in the item superclass on the right side get you closer to the MySQL schema, in case you want to query very particular details about data types and transfer that information into Python objects. Okay, so I want to zoom out a little bit and just kind of explore the decision-making process that led us to this design. Okay, so there are two ways you can design a database, right? You have the SQL and the NoSQL, or key value pairs. We want to be able to offer data assimilation scientists with a lot of flexibility in organizing their experimental data. But we also have to balance that with a sense of order and organization. So the NoSQL solution is great in a one-to-many context, and the SQL solution is great for a one-to-one context. For NoSQL, it would be very easy to ingest a data file, and for a user to add whatever tags they want to that file, willy-nilly, arbitrarily, and then form their own collections. And these collections could be subsets upon subsets upon subsets. Now, the problem there is they have free rein to design the data however they want, but you run the risk of overcomplicating your data stores and making it harder to track your data files. In the SQL environment, it restricts your tagging opportunities based on your predefined schema. But the resulting database is very interpretable. It's very easy to understand. And so if we get the next slide here. Yeah, so in the background are two sweating candidates for our database solution. One is MySQL and one is MongoDB, which is a NoSQL. And there are some factors that went into our decision that are beyond purely technical aspects of these database solutions. We ended up going with MySQL because it's very trusted, it's old and established, and there's a wide user base. So that will make it easier to maintain R2D2 in the future if we need some new contributors. Eric, would you like to add anything to this?
And so we had meetings with, since JCSDA is a research to operations project and agency, we wanted to reach out and get the blessing of the National Center for Operations. So we met with them, and it was decided to go with a standardized technology with MySQL as a good research to operations for research to operations deployment. A lot of it is if you're trying to get something into an operational software stack, that takes almost a year or two to finally get that library included. When it comes to so they were really looking for a technology that would be very well known and trusted. Of course, with MongoDB, you know, we could also append that with Redis, which uses a memory cache storage. And with Mongo, the transactions are parallel versus MySQL transactions, which are buffered and they're executed in line on the same tables.
Thank you, Eric. And you can take us home.
Yeah, sure. And so to wrap up, we'll talk about ways that we're going to be updating this deployment of this system, which is kind of in its infancy. We've only been working on it for about the past 8 months. So one of the things that we are going to do is split up R2D2 into a lightweight client and a centralized, well-maintained cloud server instance. So in this way, right now, if you incorporate R2D2's Python code into your Python code, every time you call one of R2D2's functions, each one of those functions is going to make upwards around like 10 different MySQL queries. And so you end up having like Cheyenne querying our MySQL server in the cloud multiple times for each atomic function. But what we're going to do is take the query mechanism that's in R2D2, move that close to the server, and just offer a client. And so that will make things speed up. Oh, and another reason for that we chose MySQL, even though it is a slow technology, the amount of time it takes for these MySQL queries is small compared to the data movement. And it's also small to the runtime of the executables. So that wasn't really a factor. But as we split up the R2D2 into a client server kind of architecture, we're looking at applying Flask or some other library in order to enable a secure REST API. Because right now we're having to do a lot to secure the MySQL port, and it's much easier to secure a REST service. We're also looking at going beyond the Python implementation and also developing an R2D2 CLI so you can do it from terminal. And we're also working with UCAR and UCAR's contract with AWS in order to implement RDS for MySQL, which is a paid managed MySQL service where Amazon will provide us for scalability, replication, and automated failover. From an observation point of view, from a data point of view, in conjunction with YODA, R2D2 and YODA will enable new capabilities so we can fetch data for an arbitrary time window. So right now, when you request a file from a YODA file or an HDF5 file from R2D2, you're going to get the whole file. You're either going to get a sim link to that file, or we're going to make a copy of that file. And so what we want to be able to do is usually they'll only want a small section of that file, or we're only going to want the observations that took place within the last 3 hours that are within that file. And so we want to be able to fetch data and provide a YODA file that's going to have an arbitrary time window. We also want to add channel selection. So if you look at something like GoZara, there's 16 channels on Go 16 or 17. But as of right now, we don't use the reflectance channels. We only use brightness temperature. So we would want to go ahead and just pull those channels out of there and reduce the amount of data movement. And then also talking about GoZara, of course, the native resolution for Go 16 is 2 kilometers, but that you end up having millions and millions of observations in every single cycle. So part of it is to thin that down, subsample that, and still be able to get a reasonable result without having to move so much data. And also with the data stores, we've already started looking at expanding to Microsoft Azure and the Google Cloud platform. The Air Force and Navy are very interested in us moving to possibly making sure that R2D2 is cloud agnostic. So we'll be able to pick this technology up and move it elsewhere and make it portable. Lastly, another improvement on the data stores that people have asked for over time is to integrate with high performance storage systems or the tape backup systems on HPCs. And then finally, we want to start thinking of R2D2 more than just a file manager or an access and search mechanism, but start thinking about R2D2 in the future as being a data aggregator. In that sense, we will become a data provider. So we will have to start, looking at data sets that have DOIs minted, looking at making sure we have the provenance of data sets. And like one of the earlier talks, talk about licensing, because at some point we may have proprietary data and have to be able to control access to that data. So those are some of the things that'll be coming out over the next 6 months. But thank you very much. And any questions?
If you're in the room, feel free to ask one, or if you're online, I'm looking.
Thanks for this talk. One of the big things that's enabled by toolkits and centers like this are user communities. And I'm wondering if you can give us your perspective on how the user community sees and works with and shares the capabilities that they build on this.
Oh, yeah, yeah. So the JCSDA is really a community-built organization. So we have about 35 core FTEs that work for JCSDA as UCAR staff members. But beyond that, we, through our partner agencies, and this includes Tariq's participation as well, we have over 100 in-kinds that donate their time. Sometimes it's in development and design. Sometimes it's to guide the project together. So when we pull together our requirements for the different software components that are generated underneath the JEDI effort, we have a lot of community involvement. We have quarterly meetings. We have an executive team that's made up of officials, program managers at NOAA, NASA, Air Force, and Navy. And so currently this version of R2D2 is only available internally. We're going to spend the next quarter when Skylab release version 5 comes out. We're cleaning up the software, the documentation, a few other small things, but we'll be releasing this, and then we'll be working with other agencies to implement the utilization of R2D2. One of the first utilizations outside of the Skylab application envelope is that we'll be working with NASA and NOAA to actually catalog almost 100 years of climate change data for reanalysis within the context of the R2D2 technology. And that effort, I think, is going to start within the next year. And also the UK Met Office is looking at adopting this as well as other JEDI tools. And that's within their schedule within the next year or two.
Really exciting prospects. Thanks.
Yeah, yeah. Thanks a lot.
I don't see any online. Anyone else in the room? Okay, well, let's go ahead and give all the speakers one last round of applause. I also want to give a shout out to all the past moderators and the UCAR multimedia folks for keeping this running smoothly. So thank you. Sorry. And then I want to give one final shout out. I don't know if she's listening, to Tasia Peterson, who is out there, who basically made this all happen and got us all food. So yes, thank you, Tasia.
Thank you, Tasia.
Yes. All right, so we have a break for about 30 minutes, and then we'll come back and have a discussion and or networking. So thanks. And sorry, the break is till 2:30. I don't know if I said that, but. Yeah, right. Yeah, it's I'll have to ask. Yeah. According to the thing, it's a break. Oh, I don't know. I got this schedule. Oh wait, in person. This is brief. What is this? And then it's like 3 to 4. I thought that was the discussion. 3. that's confusing. Whoops. Are we nuts with that? Damn it. Okay.